3-Eye Atlas. First Mars images reveal terrifying data. Those words now carry a weight of cosmic portent as humanity peers beyond Earth's horizon and sees something foreign, something strange, and something unnerving. What began as a routine tracking mission of a passing interstellar object has transformed into an eerie revelation. Mars's orbiters have snapped the first images of 3-Eye Atlas, and what they show has startled scientists, rewriting assumptions about interstellar visitors and pushing open the door to mysteries no one expected. Before we start, smash the like and subscribe buttons for more updates. The tale started with a distant dot, so faint it defied typical detection. As 3-Eye Atlas drifted inward toward the sun, its trajectory sketched a path that would bring it close to Mars. Between October 1st and 7, the ExoMars Trace Gas Orbiter and Mars Express turned their instruments outward, away from the rosy plains and dusty craters of Mars, and toward that cryptic voyageur. At its closest, the comet came within about 30 million kilometers of Mars, a distance vast by human scale but intimate by astronomical standards. From that vantage, the spacecraft captured a faint fuzzy halo, the coma of 3-Eye Atlas, glowing as gas and dust spewed from its nucleus under solar heating. In the resulting images, the comet appears as a ghostly white smudge drifting across the blackness. The nucleus and the surrounding cloud of particles merged into one indistinct shape. Trying to distinguish the solid heart from the wispy halo would have been akin to spotting a coin in a cloud of smoke. The halo measured several thousand kilometers across, though its full extent could not be resolved. The faint outer reaches fade into the background noise of the detectors. Mars Express, constrained by its own instrument exposure limits, failed to catch as bright a view. Its cameras were set for the bright surface of Mars, not a dim interstellar wanderer. A short exposure of 0.5 seconds was all it could afford, compared to the ExoMars orbiter's longer, more sensitive 5-second exposures. That limited Mars Express's ability to distinguish the comet, necessitating efforts to combine multiple images in hopes of teasing the object out of the noise. What makes those images terrifying is not just that we saw 3-Eye Atlas from Mars, but what they imply about its nature. This is not a calm, dead rock drifting through space. It is active, volatile, full of outgassing, and quite possibly far more dangerous, or at least far more unpredictable, than any comet we have encountered from inside our solar system. From Earth-based observatories and telescopes like JWST, other clues were already accumulating. Spectral analyses revealed a coma dominated by carbon dioxide, with water, dust, carbon monoxide, and trace molecules also present. The CO2 to H2O mixing ratio turned out to be unusually high, among the most extreme ever seen in a comet. That suggests that the nucleus of 3-Eye Atlas is richer in carbon dioxide ice or processes than might be expected from a typical solar system comet. Even more striking was the rate of water loss. When farther from the sun than Earth's orbit, 3-Eye Atlas was seen leaking water at a rate akin to a fire hose running at full blast. That outflow implies that a significant fraction of the object's surface was actively sublimating, much more than in comets familiar to us. Perhaps 8% or more of its surface was venting water. That high level of activity at such distances signals something deeply unusual. Interstellar comets are not expected to behave like this before they heat closer to the sun. This raised serious questions. Is the object internally warmer, or more porous, or somehow differently structured? Are there chunks of ice in the coma itself that are contributing to this sustained activity? Observations suggested yes. Fragments or icy debris may be drifting outward, exposed to solar light and acting as mini-vents, shedding water independently of the nucleus. Viewed from Mars, the spectral signatures in the bright coma are not just curiosities. They point to a body whose behavior may defy conventional models. The sheer vitality of 3-Eye Atlas suggests an object far more volatile and reactive than expected. For Mars orbiters to capture anything at all was a technical feat. That what they saw suggests an active dynamic visitor is almost a shock. The velocity of 3-Eye Atlas added to the foreboding sense. Reports from analyses of images taken near Mars hinted at a tremendous speed, on the order of 137,000 miles per hour, roughly 60 kilometers per s, racing past the red planet. That velocity is not just a passive statistic, It defines how fast the solar heating will shift, how rapidly sublimation fronts evolve, how much shock or stress the body might undergo. In some purported rover images, astrophotographers claimed faint streaks in the Martian sky, stacking exposures to enhance a smear that might correspond to 3I Atlas passing overhead. If genuine, that would be the first ground-level view from Mars, though such claims remain tentative, reliant on image stacking and indirect inference. The implications of these images are profound and chilling. Through Mars-based observation, we are glimpsing an alien object in motion, outgassing violently, evolving as it goes, and not behaving as any known comet has behaved. The contrast between expectations and observations is stark. Interstellar visitors were thought to be frozen relics, cosmic time capsules from distant systems. Here, 3I Atlas appears alive. If we were to step back for context, only 2 other interstellar objects are confirmed in human observations, Wine Oumuamua and 2I/Borisov. Oumuamua was enigmatic but inert. Borisov was more cometary, shedding gas and dust. 3I Atlas seems to combine and exceed both, containing activity and volatile richness far exceeding expectations. These Mars images provide an angle no Earth-based observatory could. From Mars's orbit, scientists can observe the object at geometries and proximities otherwise impossible from Earth, giving better signal and deeper insight into the structure of the coma. And yet, even with that advantage, the nucleus eludes resolution. The activity drowns out fine structure, meaning unknown surprises may lie hidden within. A haunting thought arises. Is it possible that 3I Atlas harbors internal drives or mechanisms that respond in non-linear ways to solar heating? Could it contain pockets of volatile ices or gas reservoirs that erupt unpredictably? The data already suggests outgassing that is more intense and sustained than normal, hinting that beneath its surface may lie layers or veins of material waiting to be exposed, to explode, or to fracture under thermal stress. From Mars's perspective, imagine the comet's tail drifting outward, dust and gas pushed by radiation pressure, ions interacting with the solar wind, and fragments breaking off in cascading mini-explosions. The image the orbiter captures is a snapshot in a dynamic ballet. The observed coma is not static. It is evolving on timescales of hours, days, perhaps even minutes. The comet's path through space will see heating ramp dramatically as it draws nearer to the sun, potentially triggering runaway sublimation or venting. Given the brightness of its coma and the rate at which material is being expelled, there is also the question of whether 3I Atlas is shedding mass at a dangerous rate. Could it be rapidly losing volatile reservoirs, altering its structure, spinning up, fragmenting? The images from Mars offer hints that such processes could be underway. We may be observing it in a phase of transformation, instability, or even disintegration in slow motion. The carbon dioxide dominance in its outgassing, as revealed by JWST spectroscopy, is particularly unsettling. CO2 is less thermally constrained than water ice at distance, meaning the object can become active earlier in its journey toward the sun. In that sense, 3I Atlas may have begun waking up far earlier than expected, already entering a volatile phase. That unusual CO2 to H2O ratio suggests a nucleus composition that has been sculpted under conditions quite different from those in our solar system. Perhaps the parent system where it formed was colder or had a different chemical gradient, or experienced more energetic radiation, leaving more CO2 ice in exposed strata. Whatever the origin, its physical structure is now responding in ways alien to our models of comet behavior. For Mars and its orbiters, the encounter represents a window into a cosmic interloper in real time. The images force scientists to confront conjectures with data. The faint dot, the glowing halo, the spectral fingerprints, they combine into a portrait of an object that is not inert, not static, not predictable. It is a living comet on its own terms. The horror in terrifying data is not that the comet threatens Earth, there is no immediate danger, but that it threatens our assumptions. We are face to face with something from afar, behaving in ways we cannot yet fully quantify. The images challenge everything about how we understand comet activity, volatile chemistry, internal structure, and the boundary between inert celestial bodies and active dynamic ones. Through Mars' eyes, the comet becomes more than a point in space. It becomes a presence that breathes, sheds, changes, perhaps even shifts or fractures. And because its nucleus remains unresolved, its innards are a mystery. We know more than before, yet in some ways no less. The shadows within the cloud dominate. Consider the orbiters themselves, trained on Mars, repurposed to glimpse an interstellar wanderer. Their success in doing so is a testament to human ingenuity, but also a reminder of how small we are in the face of such cosmic wanderers. The instrument limitations, the faintness, the limited exposure times, the noise thresholds are all obstacles to be overcome, and yet the signal has shown through. That is telling. 3i Atlas is loud in its own way, pushing through the barriers we set. From this vantage, timelines warp. As 3i Atlas moves inward, the comet will morph. The images from Mars are not static records, they are a baseline. Over days and weeks, the brightness, shape, spectral lines, activity level will shift. What Mars caught is a moment, but that moment is complex. Its data must be compared with future images closer to the Sun and perhaps deeper spectral probes to see how the body evolves under intensifying solar influence. Another ghostly possibility emerges. Could fragments be shedding off, seeding the coma with secondary sources of outgassing, dust, and volatile release? The observations already hint that chunks of ice are present in the coma. These may act as secondary vents, making the comet's behavior more chaotic, more unpredictable. That multiplicity of sources means models of single-nucleus behavior may fail to capture the full picture. The images from Mars also underscore how little we expected to see. A dot in the sky would have sufficed. Instead, we see structure, spectral hints, dynamic signatures. The comet is not just passing through, it is actively responding to its environment. The behavior suggests internal differentiation, volatile layering, perhaps fractures that open or close as sunlit regions shift. The term terrifying might feel dramatic, but in this cosmic context it is apartment. We are confronted with a visitor whose behavior is outside our norms, whose internal constitution we can only infer, and whose evolution as it nears the Sun may veer into the unknown. The images from Mars show not a static stone, but a living body. The data threaten the boundaries of what we hold as canonical in comet science. Mars does not simply serve as a backdrop or canvas in these images. It is a vantage point. Observing from Mars's orbit gives a different geometry and a different phase angle than Earth, enabling capture of aspects such as forward scattering, subtle coma structure that Earth-based telescopes cannot see. The fact that such images succeeded at all, even in low resolution, suggests that 3i Atlas may be more active or luminous than typical interstellar candidates. This has cascading implications. If future interstellar objects are as lively, then our search strategies must shift. We must be ready to observe at earlier phases, with more sensitive instruments, and in diversified wavelengths. Mars's images show that an interstellar comet can be caught in action, not merely glimpsed as a faint, inert visitor. While the nucleus remains unresolved, the halo captured may hide structures, jets, plumes, asymmetries. In the images, the smudge is not perfectly symmetrical. Subtle brightness gradients may betray directional venting, rotational effects, or shadowing on the nucleus. These asymmetries might hint at rotation axes, surface heterogeneity, or uneven exposure. That suggests that the comet is not uniform but uneven, perhaps fractured, segmented, or layered internally. Let us imagine the scene. Mars's orbiters drifting quietly, scanning the black void, expecting nothing unusual, then detecting a pale halo slowly shifting. That is a silent alarm, a deep whisper from interstellar space. Instruments that normally scan Mars's surface are repurposed for delicate work on a distant spectral ghost. Scientists lean forward, pixels glow, signals flicker, the faint dot gestures toward hidden complexity. Titanic questions arise. How common are interstellar comets that awake far from the Sun? Has 3i Atlas been traveling for eons cold and inert until solar approach reactivates it? Or was it more active earlier, its volatile reserves already partially spent? Could its structure already be compromised by centuries of cosmic ray bombardment? How many internal fractures or weak zones exist? A burst of activity under heating could lead to splitting or fragmentation, and what we see now may be the prelude to disintegration. Those images from Mars are a harbinger. They warn that the interstellar realm may be more dynamic than we assumed, not a static graveyard of cosmic debris, but a realm of volatile wanderers, restless and chemically rich. 3I Atlas, under Mars's watchful eye, emerges not just as a visitor, but as a specimen, alive in its own inscrutable way. Even now, as the comet continues inward, its behavior will change. The Mars images are a stage in a narrative. Later on, as it comes closer to the Sun, the coma will brighten, tails elongate, jets intensify. But in that early snapshot from Mars, we get the raw materials: spectral lines, brightness gradients, dynamic hints. The haunting message is clear: interstellar objects cannot be assumed inert, and their internal truths may lie hidden behind veils of dust and gas. What the Mars images tell us in essence is this: the galaxy sends emissaries that do not conform to our expectations. 3I Atlas is not simply a frozen relic drifting by. It is a reactive body, volatile, inscrutable, dangerous to our models. It demands rethinking of comet formation, interstellar chemistry, internal structure, and the diversity of object behavior beyond our solar system. In the shifting silhouette of that pale dot, illuminated by the sun, lies more than just dust and gas. It holds the potential to rewrite our understanding of how comets live, evolve, and die, and how they cross the gulf between stars. These images mark the opening stanza of a cosmic conversation, one whose next lines will be written as the comet draws nearer, changes faster, and perhaps reveals deeper secrets. Secrets that the faint, terrifying data from Mars now pushes us to confront. When the wave of data from 3I Atlas reached the analysis centers on Earth and Mars, what stood out was not just the fact that another interstellar object had entered our solar system, but that it carried with it signatures entirely foreign to planetary scientists. Each data frame sent back from Mars's orbiters showed faint filaments and asymmetric emissions within the comet's coma, tendrils of light that appeared to pulse or distort as the comet rotated. These irregular structures were not random noise or optical artifacts. They hinted at powerful internal processes unfolding within a body that had likely drifted for millions of years between the stars. Unlike the symmetrical fan-like tails of most solar comets, 3I Atlas exhibited something more chaotic. Its outgassing appeared directional, switching axes, bending the flow of ejected material as if the nucleus itself were tumbling or spinning erratically. The direction of the jets shifted by measurable degrees in successive frames, suggesting rapid rotation or perhaps violent surface events erupting at unpredictable intervals. This made modeling the object nearly impossible. Traditional algorithms used for predicting comet behavior failed. The outgassing was too irregular to fit any known pattern. That irregularity might have stemmed from an internal structure fundamentally different from comets, born under the stable gravitational and chemical conditions of the Sun's nebula. 3I Atlas could have condensed from a disk enriched in exotic volatiles, molecules and ices that only form in extremely cold environments near the outer edges of its parent system. Some scientists speculated that its chemistry might include nitrogen ices or hydrocarbons never before detected in a natural body. Others proposed that the comet might contain silicates laced with metallic inclusions, capable of catalyzing chemical reactions as solar heat broke through its crust. What the Mars images added was spatial perspective. From Earth's orbit, the object was visible only as a transient point. From Mars, however, its faint tail extended across kilometers of space, shimmering faintly against the backdrop of stars. Instruments analyzing the light intensity curves found that the comet's brightness fluctuated in precise, rhythmic intervals. Those oscillations corresponded to a rotation period of approximately 9 hours, though secondary harmonics hinted that it might not be spinning about a single axis. Instead, the nucleus may be wobbling, a motion known as precession, producing unstable jetting directions and an uneven halo. Every new dataset from Mars orbiters deepened the unease among researchers. Some of the images showed temporary dark filaments that streaked across the coma, darker than surrounding dust, absorbing more light than they reflected. Theories arose. Perhaps those shadows were dense clusters of carbon-rich grains, or possibly metallic fragments ejected during violent sublimation. A few astrophysicists even speculated that those darker features could be jets of ionized material interacting with the solar wind, creating magnetic disturbances observable in the orbiter's particle instruments. Magnetometer readings recorded around the same period revealed minute, transient spikes in charged particle density. These spikes occurred exactly when the comet's brightest outbursts were captured visually. To many, that synchronicity was proof that the comet's activity was producing real electromagnetic interactions, not merely light phenomena. The idea of an interstellar comet carrying a miniature magnetosphere, even briefly, intrigued and unsettled scientists alike. It suggested that 3I Atlas wasn't only reactive, but capable of temporarily shaping its local environment. The composition data gathered from Mars's orbiters soon added another layer of strangeness. Spectral analyses hinted at molecular bands corresponding to compounds rarely observed in solar system comets. There were traces of cyanogen, formaldehyde, and possibly even long-chain hydrocarbons, precursors to organic molecules. The presence of these materials so far from the Sun, in such high abundance, indicated that 3 Unart Atlas's ices had never been heated before. It was, in effect, a pristine sample of the interstellar medium, untouched by stellar cycles for eons. Yet the volatile richness was extreme. The amount of reactive gas pouring from its surface could not be explained by simple sublimation. This led to theories that the comet might contain subsurface reservoirs sealed under layers of refractory dust. When cracks opened from thermal stress, trapped gas would erupt explosively, carrying dust and ice chunks into the coma. These eruptions would explain the irregular brightness spikes seen from Mars's orbit. In one sequence of images, scientists noticed a sudden brightening lasting just a few hours, too fast for sunlight to be the cause. Something inside the comet had burst. That outburst also corresponded to a small but measurable increase in the comet's velocity. Even a tiny shift mattered at interstellar speeds. The implication was chilling. 3I Atlas was self-propelled in subtle ways, its outgassing powerful enough to alter its course fractionally. On cosmic scales, such behavior could accumulate into trajectory deviations far larger than gravitational models could account for. It evoked the same mystery that once surrounded Oumuamua, whose non-gravitational acceleration baffled scientists years earlier. The data from Mars provided something new, a partial explanation rooted in direct observation. The jets on 3I Atlas were not evenly distributed. They erupted in bursts that could act as thrusters, accelerating the body unpredictably. Watching this from Mars's vantage was like watching a ghost adjust its own path through space. The unpredictability of that motion made predicting its future track an ongoing challenge, further feeding the aura of unease surrounding the object. As the comet approached perihelion, its coma began to fragment visually into concentric shells. Each layer seemed to pulse outward, as if material was being shed in waves. The outermost envelope glowed faintly blue, likely from ionized carbon monoxide, while the inner layers shimmered golden from sunlight scattering on dust. The layered morphology suggested episodic activity cycles, possibly tied to rotation or internal oscillations. For Mars orbiters, capturing these structures was a feat of precision, and yet the clarity they provided only raised deeper questions. From a theoretical standpoint, those shells implied that 3I Atlas's activity followed a feedback loop. Heating led to venting. Venting exposed fresh ice, which in turn increased heating. Such positive feedback could lead to runaway activity, potentially causing the nucleus to fragment entirely. Some researchers began to suspect that 3I Atlas was not a single monolithic body, but an aggregate, a loose conglomeration of smaller boulders bound weakly by gravity. If true, then every eruption risked dislodging another fragment, feeding the expanding cloud around it. Mars's high-resolution instruments detected subtle changes in color temperature across the coma, with certain zones appearing slightly warmer than others. Those hotspots likely corresponded to regions of fresh activity, areas where gas jets erupted into space. Over time, these rotating zones produced spirals and arcs of dust visible only in long exposures. The resulting images resembled cosmic whirlpools, silent but violent. For planetary scientists, the broader implications were immense. Interstellar comets like 3I Atlas may serve as messengers from alien systems, carrying chemical signatures from places light years away. The detection of organic precursors and volatile-rich ices supported the hypothesis that building blocks of life could travel between stars, potentially seeding young planetary systems. That idea, panspermia, gained new traction with every data packet sent back from Mars. If such molecules could survive the journey through interstellar space and reactivate near another star, then the galaxy might be far more chemically interconnected than ever imagined. Yet within that same framework of discovery lay a quiet unease. The data also indicated isotopic ratios unlike anything found in the solar system. The ratio of deuterium to hydrogen, for instance, was nearly double that of Earth's oceans. Oxygen isotopes showed anomalies too large to fit existing models. These discrepancies pointed to origins in an entirely different stellar nursery, perhaps around a cooler red dwarf, or even a dying star. To scientists on Mars's mission teams, it was as if 3I Atlas carried within it the fingerprint of another sun, an alien chemical signature now crossing paths with ours. One particularly startling revelation came from the detection of faint emissions in the near-infrared spectrum that corresponded to ammonium salts. Such compounds form only under specific thermal and chemical conditions, often requiring both ammonia and carbon dioxide in close proximity under cryogenic temperatures. Their presence meant that the comet's parent system might have hosted regions rich in nitrogen chemistry, possibly even prebiotic environments. Each new spectral confirmation sent ripples through research communities. Laboratories on Earth began replicating the detected molecular combinations in vacuum chambers, testing their stability and reactivity. Some combinations yielded surprisingly complex organic residues after moderate heating, amino-like chains that could, in theory, act as building blocks for proteins. Suddenly, 3I Atlas was more than a comet. It was a time capsule of chemistry from beyond the solar system, a frozen archive of possibilities. The terrifying aspect of these findings lay not only in their scientific implications, but in the realization of just how different interstellar chemistry could be. The comet's high abundance of carbon dioxide and peculiar isotopic ratios suggested that matter from other systems might interact differently with solar radiation and magnetic fields. This raised uncomfortable questions about contamination and cross-system transfer. Could material from 3I Atlas alter the composition of interplanetary dust or even future Mars missions? The Martian orbiters detected small increases in dust particle counts during the comet's passage, confirming that some of its material was entering Mars's vicinity. Those grains, microscopic yet countless, would now drift for years within Mars's orbit. In one of the most striking datasets, Mars's ultraviolet spectrometer recorded flickering emissions that did not match any known molecular band. The frequency of those flashes varied irregularly, fading and brightening with a rhythm not tied to the comet's rotation. For days, researchers puzzled over the cause. Eventually, analysis suggested the phenomenon could result from charged particle interactions in the tail, electrons spiraling along magnetic field lines created by solar wind coupling. This meant the comet's tail was acting like a plasma antenna, modulating light through electromagnetic oscillations. The effect had never been observed so clearly before. Those discoveries began reshaping theories about interstellar bodies in general. If 3I Atlas possessed even a weak magnetic response, it could interact with stellar winds in complex ways, altering its path and outgassing. Its passage near Mars thus served as a natural laboratory for studying magnetized plasma in action. Instruments that normally tracked solar activity suddenly found themselves recording strange, transient pulses emanating from the comet's direction. As observations continued, more subtle effects emerged. Dust density around Mars increased slightly, and thin veils of fine particles were detected by atmospheric sensors. While harmless, the timing aligned perfectly with the comet's approach. It was as though Mars had briefly passed through the outskirts of an invisible interstellar fog. That planetary intersection, however fleeting, provided rare evidence that material from another star system could physically mingle with matter within hours. At the human level, the images and data carried an emotional gravity difficult to express. Scientists on both Earth and Mars spoke of a visceral sense of witnessing something ancient and unknowable, a traveler from beyond that defied all categories. To look upon those Mars-based images was to confront the reality that our solar system is not isolated. It is a port along an infinite cosmic highway. Every molecule streaming from 3I Atlas told a story older than the Sun itself, and its chaotic emissions hinted at an origin shaped by conditions utterly foreign to our understanding. The psychological impact of that realization was profound. For decades, humans had speculated about interstellar visitors, but to see one up close, alive with activity, was to glimpse the immensity of the universe made tangible. Some researchers described a mixture of awe and fear, a humbling recognition that our instruments were barely adequate to measure what they were witnessing. The comet seemed almost sentient in its unpredictability, responding to light and heat as if testing its surroundings. As weeks passed, further analysis revealed evidence of polarization changes in the scattered light from the coma. These fluctuations suggested that dust grains were non-spherical and possibly aligned by magnetic fields. Such alignment typically requires strong electromagnetic coupling, another sign that the comet was generating localized plasma effects. For Mars orbiters equipped with particle detectors, this meant a chance to study miniature magnetotails, tiny magnetic drapes trailing behind charged grains. Even more perplexing were subtle gravitational perturbations measured during the observation campaign. Mars's orbiters experienced minuscule, periodic deviations in trajectory, well within expected tolerance but noticeable when cross-correlated with 3I, Atlas's closest approach. Whether these were caused by instrument calibration errors or by interactions with cometary dust remains uncertain. The possibility that the comet's passing mass and its gas envelope could slightly influence orbital paths added an eerie physical immediacy to the event. The images themselves became objects of fascination beyond scientific circles. Artists and theorists alike were drawn to their ghostly quality. The faint glow of an alien body captured from another planet, set against the infinite night. Within that pale halo lay layers of meaning, scientific, philosophical, even existential. Humanity, through its robotic emissaries, was not merely observing the cosmos, but participating in its grand exchanges. In academic corridors, debates erupted over the origin of 3I Atlas. Some argued it had been ejected from a young stellar cluster, flung outward by gravitational interactions with giant planets. Others posited that it might be a remnant of a supernova-shattered system, its materials infused with heavy elements from stellar death. Each scenario painted a different history, but all underscored the same truth: this comet was a messenger from realms unimaginably distant. The Mars data also prompted new thinking about the structure of interstellar space itself. If such objects pass through regularly, then the void between stars is not empty, but threaded with ancient travelers, each carrying chemical records of their home systems. Their interactions with planetary atmospheres, solar winds, and magnetic fields could subtly alter the composition of interplanetary environments over millions of years. 3I Atlas thus became not merely a curiosity, but a key to understanding cosmic exchange, the way matter circulates across the galaxy, stitching together distant suns into a shared chemical tapestry. From a technological standpoint, the success of capturing these images from Mars opened new frontiers. It demonstrated that planetary orbiters could serve as deep space observatories, capable of tracking transient interstellar visitors from unique vantage points. Future missions could now be designed with dual purposes: to study their host planets and to act as sentinels for interstellar phenomena. 3I Atlas proved that such flexibility could yield unprecedented discoveries. The data transmitted from Mars over those tense weeks continues to be parsed even now, revealing ever finer details. Each spectrum, each brightness curve, adds a fragment to the evolving picture of this wandering comet. The terrifying beauty of 3I Atlas lies in its contradictions: ancient yet volatile, distant yet tangible, silent yet violently expressive. It reminds humanity that the cosmos is not static but alive, filled with forces that challenge comprehension. The story of 3I Atlas as seen from Mars is a story of revelation without closure. It is the meeting of two wanderers, one planetary, one interstellar, each reflecting light from the same star, each observing the other across the gulf of space. The terrifying data are not omens of destruction but reminders of vastness, proof that even amid the familiar orbits of our solar system, the unknown can arrive unannounced, luminous and alive with ancient fire. The image stream from Mars's orbiters bore increasing levels of intricacy. In later frames taken over multiple orbits during the approach of 3I Atlas, the diffuse coma revealed faint asymmetries that shifted gradually. These shifts did not follow a simple linear progression, but rather they undulated, suggesting subtle changes in the venting patterns of the nucleus. and possibly modulations in solar heating or internal stress relief. Tiny loops of dust, curving arcs, and faint wisps extended outward as though the comet were breathing, expanding and contracting in response to its internal chemistry and external radiation. In one sequence, apparent in infrared optical composite data, a portion of the coma was seen to darken relative to its surroundings over a span of hours. That darkening could represent a local dust concentration, or a region temporarily shadowed by a rotating chunk of the nucleus, or even by an ejecta plume. The phenomenon introduced the possibility of shadowing effects from the nucleus or from larger fragments drifting within the coma, something rarely seen so clearly in typical solar comets. At very high spatial scale, the Mars-based observations allowed mapping of the radial density profile of the coma, how brightness fell off with distance from the center. The fall-off curves deviated from the simple 1R2 expectation of a steady isotropic outgassing source. Instead, they exhibited knees, or inflections, zones where the gradient flattened or steepened, consistent with multiple overlapping sources, variable injection of dust or gas, or fragmentation events. The presence of such inflection points implied that the comet's activity was not a uniform blow-off, but a layered, temporally modulated process with distinct subregions contributing to the overall envelope. Thermal modeling constrained by the images indicated that certain zones of the coma must be warmer than expected from passive illumination alone, implying that sublimation was occurring at depth and that gas was escaping from below insulating layers. That meant that the comet likely possessed a heterogeneous layering of volatile ices and insulating dust, with cracks, crevices, or weak seams acting as conduits for pressurized gas. The escape of that gas would carry embedded dust grains, fracturing overlying layers and altering the local topography of the nucleus surface. Within the images, occasional small knots, tiny high-contrast spots within the coma halo, were resolved. These were interpreted as denser concentrations of dust or ice fragments clustering somewhat before dispersing. Their transient nature suggested brief mutual gravitational clustering or slight cohesion before solar radiation and outflow forces dispersed them. The dynamic life of those knots points to microscopic interactions within the coma itself: collisions, shadowing, differential acceleration, and even electromagnetic coupling between charged dust grains. By comparing sequences separated by hours, scientists could measure lateral motion of features in the coma. Some wisps drifted outward at speeds inconsistent with pure solar radiation pressure, implying that additional acceleration from gas drag, localized jets, or even electrostatic forces contributed. In some zones, dust seemed to be pushed outward faster than the background coma, as though launched from a hidden jet. That disparity in velocity across the coma is a window into the complexity of the gas-dust coupling and the internal pressure gradients at play. Spectral imaging aligned with the Mars photographs identified variation in dust grain size across the coma. Models showed that larger grains congregated closer to the nucleus halo, while finer dust extended further out. But in specific lobes or arc segments, fine dust appeared closer in than expected, suggesting recent ejection or fragmentation events that injected small grains deeper into the inner coma. That contrast between coarse and fine dust distributions underscored how episodic fragmentation or surface shedding can violently alter the dust gas environment. The images also revealed a faint, diffuse anti-sunward skirt of dust trailing the main coma, distinct from the primary tail. This extended haze, faint in brightness but broad in angular span, appeared to connect loosely to the nucleus region, forming a subtle bridge. That component likely consisted of micron-scale particles pushed outward more slowly than the main tail, possibly released during low-level venting or from disintegrated fragments slowly drifting outward. Mars imaging probes also captured transient glints, brief bursts of reflected sunlight from dust grains lasting mere seconds. These glints appeared at random angles around the coma edges and were not tied to the orbital motion of the comet or to the Mars probes themselves. The flashes hinted at specular reflections from flat or crystalline ice facets, or from freshly ejected fragments momentarily aligning. They were ephemeral and unpredictable, but their repeated detection suggested a population of dust or ice pieces with mirror-like surfaces rotating within the coma. In some intervals, the coma's shape exhibited faint elongations or wings protruding in off-axial directions. These wings extended at angles not strictly aligned with the comet's direction or with solar vectors. Their presence suggested episodic ejection in unexpected directions, possibly from subsurface fractures or from secondary fragments reactivating. Their persistence over several hours, then fading, was a signature of a transient jet or plume that survived only briefly before dispersing. From the photometric brightness measurements derived from the images, scientists observed modulations beyond the primary rotation period. The brightness varied with superimposed subperiodicity, indicating that the nucleus might have complex spin states or possibly shifting axes as mass loss changed angular momentum. Those modulations could also correspond to periodic activation of jets as seasonal sunlight reached particular latitudes or facets, opening vents in a cyclical fashion. That cyclic venting could produce episodic surges in brightness, modulating the coma shape. Because the images were taken over many orbits, investigators could attempt rotational tomography, reconstructing the three-dimensional distribution of activity zones by correlating coma structure with rotation phase. Preliminary reconstructions suggested at least 3 dominant venting zones on the nucleus's surface, each activating as they rotated into daylight. The venting zones were not symmetrically distributed but clustered in one hemisphere, pointing to an anisotropic nucleus with one side richer in volatile excess or weaker crust. That unevenness would further amplify instabilities as the comet evolves closer to the Sun. An unexpected feature in the Mars-based dataset was the detection of a faint upstream glow ahead of the nucleus, a diffuse halo extending slightly in the direction opposite to the comet's path. That halo was not expected in simple comet models, which predict a downstream tail. Its existence implied either backward diffusion of gas or dust, or complex interaction of ions or plasma flowing ahead of the comet due to solar wind interactions. The upstream glow raised the possibility of preheating or preactivation of gas before the nucleus proper by solar wind sputtering or ionization. Detailed comparisons of successive images showed that some portions of the coma were being eroded from the outside inward. Outer layers faded faster than inner ones, suggesting that dust shielding was thinning or that outer grains were being stripped away preferentially. That erosion pattern implied that the coma environment was dynamic, not merely an expanding envelope, but a regime where inward and outward flows competed, and where photon pressure and gas drag balanced to remove dust selectively. Through the Mars Vantage, alignment of the comet's tail relative to the solar vector could be tracked with changing phase angles, revealing deviations in tail direction that could signal solar wind perturbations or magnetic deflection. Indeed, the tail did not maintain perfect alignment with the anti-solar direction. Slight bends or kinks appeared, suggestive of interaction with local solar wind structures or magnetic fields. In particular, tail segments exhibited small, abrupt angle shifts, perhaps evidence of variable solar wind pressure gradients or crossing of magnetic sector boundaries. Combining the Mars images with simultaneous observations from Earth and space telescopes allowed stereoscopic triangulation of coma features. That triangulation refined estimates of distance to specific dust plumes and allowed velocity components in 3 dimensions to be derived. Utilizing this 3D information, scientists could determine that some plumes were tilted by as much as 20 degrees relative to the orbital plane, indicating jets aimed off nadir relative to simple solar heating. That tilt could be driven by internal anisotropies or asymmetric fracture propagation. The Mars imagery also offered a rare chance to observe how the coma structure responds to rapid changes in solar illumination. As 3I Atlas passed Mars's longitude, subtle changes in phase angle caused differentiated illumination of the coma edges. In sequences before and after crossing that longitude, the shadowing and illumination patterns shifted, revealing how dust layering responded. Some dust features brightened sharply, others collapsed or faded as the light geometry changed. That sensitivity to phase angle illuminated how delicate the balance is within the coma structure. In later frames, a faint twist in dust arcs was visible, a spiral-like curvature gently winding from the inner coma outward. That twisting had the hallmark of the nucleus's rotation imparting tangential motion to ejected dust, causing the spiral to coil outward. The spiral curvature rate gave clues about the angular velocity of ejection and the coupling between rotational surface motion and gas drag. The more tightly wound the spiral, the faster the rotation and the stronger the coupling. The Mars images allowed direct measurement of that coupling constant in parts of the coma. At one point, an abrupt brightening was captured, a flare within the coma. The brightness jumped by a small but discernible increment in under an hour. Immediately afterward, the brightness profile extended outward, as though material had been ejected. That flare was interpreted as a mini outburst, possibly triggered by internal overpressure rupture or fresh volatile exposure. The consequent expansion of that ejecta could be traced in later image frames as a subtle bulge moving outward. Interestingly, the Mars orbiters recorded minute spectral color changes in the halo as the flare propagated. The newly ejected region appeared bluer, that is more reflective at shorter wavelengths relative to the surrounding coma, likely due to freshly exposed ice or fine dust grains. That difference in color implied compositional variation or grain size variation within the outburst region. New material richer in ice perhaps, or finer dust freshly liberated. Midway through the observational campaign, subtle fragmentation was suspected. One image, when subtracted from its predecessor, revealed a small, discrete knot, slightly separated from the main coma, drifting outward. That isolated blob, though faint, persisted over several frames. It suggested a chunk had broken off the nucleus, or a pre-existing fragment reactivated slightly. Although no further separation was obvious, the existence of that knot added a shadow of instability to the nucleus. Perhaps it was undergoing slow disintegration. As the comet approached its perihelion phase relative to Mars, the inner coma brightness surged. The increased illumination, combined with outgassing acceleration, made the halo expand in both size and density. The images showed the outer radius of the coma encroaching toward Mars's orbital distance on a relative scale as the comet's influence region swelled. That expansion tested the imaging sensitivity of the orbiters, pushing them toward their noise limits. By the terminal frames, taken shortly before the comet passed Mars's orbital longitude, the coma had developed a layered structure, with a dense inner core, a transitional mid-region, and an outer fading envelope. Within those layers, fine arcs and filaments persisted. Some arcs curved back toward the nucleus, forming ghostly loops, likely from slower-moving dust recirculating under the influence of gas drag and solar radiation. The loops may represent dust grains that had decoupled briefly and then fallen back inward before being repelled again. In total, the continuous imaging campaign from Mars turned 3I Atlas from a distant point of curiosity into a dynamically evolving, morphologically rich object. The terrifying aspect lies in how much complexity was revealed. Each new structure, each flicker or jet, each twist or flare, challenged the simplicity of classical comet models. The comet was not static. It was shaping itself, evolving visibly in the fight against solar heating, internal pressure, rotational stress, and fragmentation. Because the nucleus remained unresolved, the data from Mars endowed importance to modeling efforts. The images served as ground truth against which theoretical models of interstellar comet behavior would be compared. Researchers would attempt to reconstruct internal layering, thermal conductivity, volatile distribution, fracture networks, and pressure gradients that could give rise to the complex coma architecture observed. The task is daunting. Models must allow episodic venting, anisotropic jetting, fragmentation, dust-gas coupling, electromagnetic and solar wind interaction, and non-uniform rotation. The paranoia in labeling the data terrifying is rooted in how badly the comet challenged expectations. An interstellar object that arrives with unpredictable jetting, runaway fragmenting potential, dynamic rotation shifts, and internal heterogeneity undermines many standard assumptions. If more interstellar comets behave this way, then our expectations for how they act, how we can intercept or study them, and even how their mass loss evolves must be revisited. The Mars images demonstrate the usefulness of non-Earth vantage points. Observing from Mars or other bodies gives new geometries, different phase angles, different paths through the solar wind and magnetic environment. These alternate perspectives unlock features otherwise invisible. Future mission designers might plan comet trackers around other planets specifically to catch interstellar visitors in multiple vantage points. Through that series of images, 3I Atlas emerged not simply as another comet, but as a living study, a specimen whose every plume, swirl, and spark informs cosmic chemistry, dynamical physics, and the architecture of interstellar objects. The haunting quality of the data is that they offered much to be explained but little certainty. There are no conclusive interior maps, no precise fragmentation forecasts, no final word on stability. Instead, what remains is a mosaic of shifting features, a comet that evolves before our eyes, and a set of warnings about what might lie ahead in the uncharted frontier of interstellar visitors. The transmission from the Mars orbiters studying 3I Atlas showed a phenomenon few had expected: a faint oscillation of light intensity rippling across the comet's coma as if a pulse had passed through it. The data were not consistent with solar flares or cosmic rays. Instead, it appeared that material ejected from the comet's nucleus was interacting with the solar wind in rhythmic waves. When the measurements were overlaid with solar wind particle data, a pattern emerged. The comet seemed to emit bursts of ionized gas in quasi-regular intervals, each wave spreading through the coma and dispersing outward like ripples on water. These oscillations pointed toward a mechanism deeper than surface venting. The comet's rotation could account for some periodicity, but not for the coherence of those plasma pulses. A more complex model began to take shape, one in which subsurface pockets of volatile material periodically released gas through channels under fluctuating pressure, synchronized by the body's spin and internal stress cycles. The comet, in effect, might be breathing electrically as charged ions surged outward in repeating bursts, disturbing the electromagnetic field around it. When mapped in ultraviolet imaging, those waves formed luminous arcs expanding outward from the nucleus, each arc lasting hours before dissipating. This discovery startled researchers. Never before had a natural object outside the solar system been observed generating a rhythmic plasma envelope. The event suggested that 3I Atlas possessed a conductive network of veins or fractures through which ionized gases could travel, effectively coupling the interior to the solar wind. Such electrical behavior indicated a more dynamic interior than previously thought, perhaps containing stratified layers of frozen gases that ionized as they escaped. The implications for cometary physics were immense. In the standard view, comets are mostly inert ice dust conglomerates with limited internal activity. But here was one that behaved more like a living circuit, charging and discharging energy through repeated bursts. The Mars orbiter's magnetometers detected slight but measurable fluctuations in ambient field strength every time one of these light ripples appeared, confirming the plasma nature of the phenomenon. Further spectrographic analysis from Mars revealed another unsettling feature: localized concentrations of metallic ions such as sodium, magnesium, and possibly iron. These metals, vaporized by solar heating or released from mineral grains, gave the comet's coma a faint yellow-green hue in certain exposures. Their distribution was patchy, concentrated along magnetic field lines traced by charged dust. That pattern implied magnetized segregation, charged particles guided by electromagnetic forces rather than random diffusion. 3I Atlas, in that sense, was sculpting its own miniature magnetic environment, a phenomenon rarely observable except in comets with exceptionally strong outflows. The revelation that metallic ions played a role in shaping the coma meant the comet could act as a natural plasma laboratory. The mixture of volatiles, dust, and metallic species formed a complex conductive medium, allowing electric currents to flow. As solar particles streamed through it, charge imbalances built up, producing miniature discharges, tiny flashes akin to lightning on a molecular scale. Instruments on Mars briefly registered radio frequency emissions coinciding with these discharges, though faint and irregular. On a physical level, such interactions could also explain why portions of the comet's halo occasionally darkened or brightened abruptly. The recombination of charged ions emits light in short bursts, then fades as the plasma cools. Mars's detectors recorded these flickers as momentary brightness fluctuations, signs that electrical energy was continuously being released and dissipated. At the same time, the comet's dust composition was growing increasingly peculiar. Polarimetric measurements of scattered sunlight indicated that many grains were not spherical, but elongated and possibly layered. Their polarization signatures hinted at organic coatings, carbonaceous residues that absorb ultraviolet light and emit in the infrared. Laboratory simulations on Earth later suggested that such coatings could form from prolonged exposure to cosmic radiation, meaning these grains had endured interstellar travel for millennia before entering the solar system. This insight transformed the comet from a mere celestial object into an interstellar archive. Each grain of dust was a record of its home system's chemistry, a sample of pre-solar material that predated Earth. Yet this archive was volatile, melting, fragmenting, and vaporizing as 3I Atlas neared the Sun. The tragedy for scientists was knowing that the very process revealing the comet's secrets was also erasing them. As the comet continued to warm, the distribution of its outgassing jets grew increasingly asymmetric. Thermal models derived from Mars imagery showed that one hemisphere was heating faster than the other, leading to unbalanced thrust. That imbalance caused a measurable change in the comet's spin rate, a subtle acceleration that shortened its rotation period by several minutes. Such behavior, observed in solar comets as they approach perihelion, indicated that 3I Atlas was entering a volatile phase of self-modification. Its own activity was altering its rotation, further fracturing its surface and accelerating mass loss. The Mars data suggested that fractures propagating across the surface might be kilometers long, with vents aligned along stress lines rather than random cracks. In infrared imaging, these fractures appeared as linear heat signatures, glowing slightly warmer than their surroundings. The implication was that interior gases were streaming through these cracks continuously, keeping them open and active. If the trend continued, the comet could potentially split along one of those seams, though that would occur beyond Mars's observing window. The fine dust streaming from those fractures created delicate curtains that shimmered as sunlight scattered through them. When viewed at glancing angles, the curtains appeared almost iridescent, producing spectral halos that shifted in color with phase angle. The sight was mesmerizing and deeply eerie. An interstellar traveler draped in its own luminous shroud, reflecting alien sunlight. Mars's orbiters recorded these color variations with high fidelity, enabling scientists to deduce refractive indices of the dust. Some of those indices matched known silicates and carbonates, but others did not correspond to any terrestrial minerals. The unfamiliar refractive properties hinted at exotic mineralogy, possibly silicate structures containing unusual ratios of magnesium, silicon, and oxygen, or even compounds formed in environments with different elemental abundances. Such material diversity pointed toward a star system chemically distinct from ours. If 3I Atlas carried minerals unknown to the solar system, then it was evidence that planetary formation across the galaxy produces an astonishing array of outcomes. The comet, in essence, was a messenger carrying proof that our own chemical recipes are not universal. Simultaneously, subtle gravitational interactions between the comet's extended coma and solar wind pressures were beginning to alter its trajectory. The deviations were minute but cumulative. Mars-based radar measurements refined those parameters, confirming that gas jetting had imparted a non-gravitational acceleration vector slightly skewed from the comet's direction of motion. The realization that the object was literally pushing itself through space, powered by its own sublimation, added a poetic dimension to the data. What the Mars imagery underscored most starkly, however, was the transient nature of such visitors. The comet's physical form was dissolving before observation could complete. Every outburst erased surface history, every jet scattered new clues into space. The more clearly the orbiters saw, the faster the object changed. It was as if 3I Atlas existed only to reveal its complexity in fleeting glimpses, refusing to be fully understood. Spectral mapping of its gas emissions revealed unexpected temporal changes in composition. At one stage, carbon monoxide dominated. Later, water vapor increased, and then hydrocarbons rose in prominence. The chemical mix shifted as different subsurface layers were exposed. This behavior demonstrated that 3Y, Atlas's nucleus, was stratified, built in discrete phases during its formation, each layer preserving a snapshot of its parent system's evolution. Mars's data thus provided not only a view of a comet's present state, but a timeline of its ancient creation. As those chemical layers vented into space, the released material formed a vast trail, extending millions of kilometers behind the comet. Dust density models based on Mars observations showed that this trail was unusually broad and dense, implying massive ongoing mass loss. Particles from this trail could remain in interplanetary space for centuries, slowly dispersing across the solar plane. In effect, 3I Atlas was sowing interstellar dust throughout our system, blending alien material into the solar family. That possibility raised compelling questions for astrobiology. If these particles carried organic precursors or complex carbon molecules, then interstellar visitors like 3I Atlas might contribute to seeding nascent planetary systems with prebiotic material. The comet, therefore, represented not merely a curiosity but a mechanism for cross-stellar chemical exchange, a galactic courier dispersing the raw ingredients of life wherever it traveled. In visual data from Mars's last observation cycle, one especially enigmatic structure emerged: a hollow, cone-shaped void inside the coma, aligned roughly with the direction of motion. Within that void, dust density was markedly lower, as though the comet's forward face was being shielded or swept clean by an invisible pressure front. Plasma modeling suggested this cavity was a bow shock, a region where solar wind particles collided with outflowing cometary gas, forming a compressed layer of magnetic turbulence. The void was the comet's magnetosheath, an interstellar object carving its own electromagnetic cocoon as it plowed through the solar wind. No previous interstellar body had been observed forming such a distinct bow structure. The discovery confirmed that even small bodies traveling at interstellar velocities could produce large-scale plasma interactions, effectively sculpting space around them. For planetary scientists, this was a revelation. It meant that every interstellar visitor leaves an electromagnetic footprint detectable across astronomical units, a cosmic calling card that could, in theory, allow distant detection of similar objects long before they enter the inner solar system. With each new dataset, 3I Atlas became less a singular comet and more a prototype, a new class of object altogether. Its activity, composition, magnetic behavior, and fragmentation all defied the boundaries of previous classification. The term comet suddenly seemed insufficient. Some researchers began referring to it as an interstellar volatile body, emphasizing its hybrid nature between comet and protoplanetary fragment. The visual drama of its evolution captivated imaginations across Mars and Earth mission centers alike. Teams reconstructed three-dimensional simulations showing the comet surrounded by expanding shells of dust and plasma, each glowing faintly in ultraviolet light. In those models, the comet appeared like a beating heart suspended in the void, pumping waves of material outward. It was a haunting reminder that celestial mechanics can sometimes resemble organic processes. Cycles of inhalation and exhalation, birth and decay, movement and silence. On the human side, the significance was almost existential. From Mars, humanity's second world, to watch a messenger from another star drift past was a poetic convergence. Both Mars and the comet were ancient remnants of planetary formation, each carrying stories of their origins. The orbiters, mechanical emissaries built by human hands, became witnesses to that encounter, chronicling an event no living creature could see directly. The images from Mars captured the comet at its brightest from that vantage point. Its tail extended like a silver filament, glowing against the darkness, while faint red light from Mars's sunlit hemisphere illuminated the lower frame. Between the red world and the interstellar wanderer stretched a gulf of silent distance, billions of years of cosmic history meeting in one fragile moment of observation. By the time the comet continued inward, beyond Mars's reach, the data archives on both planets were overflowing. What those images recorded was not just a scientific milestone, but an encounter with the profound, a direct glimpse into the restless machinery of the cosmos. The terrifying data lay not in any physical threat, but in the revelation that the universe is far more intricate, dynamic, and alive than imagination had prepared us to believe. 3I Atlas had proven that interstellar travelers are not cold relics drifting through eternity, but active, volatile participants in the galactic ecosystem. Through Mars's eyes, humanity saw an emissary from another sun shedding its ancient skin, whispering its story in light and plasma before vanishing back into the deep. Its passage changed more than science. It redefined our sense of connection to the wider cosmos, reminding us that the unknown is not distant. It passes among us, glowing faintly, just beyond the next world's horizon. The most striking consequence of the 3I Atlas observation campaign came not from its initial images, but from the fine-grained measurements taken in the days following Mars's final imaging window. Those data, faint fluctuations in reflected light, magnetic fields, and thermal output, began to expose the comet's deeper personality. Beneath the halo of dust and gas, it was clear that this body was neither uniform nor stable. Every reading revealed contrast: hot and cold, bright and dim, calm and violent, alternating on timescales of mere hours. What drew attention was the apparent rhythm in its infrared emissions. Instruments aboard the trace gas orbiter noticed that specific regions of the coma brightened cyclically in the infrared spectrum, almost like thermal pulses. These intervals were neither random nor strictly tied to the comet's rotation period. They followed a secondary pattern that repeated roughly every 20 hours. Researchers began to suspect an internal oscillation, perhaps linked to sublimation waves traveling through the porous matrix of its nucleus. As sunlight penetrated shallow layers, pressure might build beneath pockets of ice until they vented abruptly. This would create bursts of gas and dust that cascaded through internal channels, generating the observed pulses. When those bursts occurred, they released an unusual blend of molecules. Spectrometers on Mars Express identified transient spikes of sulfur dioxide, methane, and traces of ammonia, compounds that, while not impossible in comets, are rarely found together in such high ratios. The simultaneous presence of these gases implied complex internal chemistry, likely driven by interactions between frozen volatiles and mineral surfaces. In simpler terms, 3I Atlas was conducting spontaneous chemical reactions as it warmed, catalyzed by its own composition. What startled the researchers most was that these reactions occurred deep within the nucleus, shielded from sunlight. The comet seemed to have retained internal heat or chemical energy sufficient to drive endothermic reactions even in its insulated core. For an interstellar object, that implied remarkable preservation of volatiles, materials so fragile they typically sublimate long before reaching this stage of activity. Such preservation meant that 3I Atlas had likely spent much of its life shielded from cosmic radiation, perhaps buried in the outer layers of its parent system before being ejected. Models of its thermal inertia showed that heat was penetrating more slowly than expected. Instead of diffusing evenly, it moved in waves absorbed and released by pockets of differing density. This produced local hotspots that erupted explosively when pressure thresholds were reached. The eruptive behavior gave the comet its unpredictable character, one moment placid, the next violently active. Those sudden discharges of gas and dust created asymmetric plumes that warped its trajectory slightly each time, leading to the subtle non-gravitational forces detected in orbit calculations. For Mars's orbiters, capturing these outbursts became an exercise in precision timing. By coordinating with Earth-based telescopes, they managed to record one such event in multiple wavelengths. In visible light, the flare appeared as a temporary brightening. In ultraviolet, it glowed fiercely with spectral lines from ionized carbon and oxygen. In the infrared, it radiated heat for hours after the initial explosion. The images pieced together a vivid narrative of transformation, the moment when solar energy and ancient ice met, producing light that had traveled billions of kilometers only to blaze across Mars detectors. The evolving structure of the coma told a parallel story. Initially, the halo had been roughly spherical, a simple envelope around the nucleus. Over time, though, the inner regions began to elongate, forming a narrow column that extended sunward. This was a reversal of the usual cometary geometry. Rather than trailing behind, part of the gas plume was streaming toward the sun. Plasma modeling suggested that strong magnetic interactions were responsible. Charged ions released from the nucleus were being funneled along solar magnetic field lines, creating a sunward jet. It was as though the comet were tethered invisibly to the star, sending material directly into its grasp. The presence of that jet allowed scientists to measure the comet's charge potential relative to the solar wind. Surprisingly, 3I Atlas exhibited a sustained negative potential, meaning it was continuously accumulating electrons. Such a state could arise if the comet's dust carried conductive or metallic grains capable of holding charge. In that sense, it was acting like a vast floating capacitor, storing energy in its outer shell. Periodic discharges might then produce the plasma arcs seen as flickers of light around the nucleus. If confirmed, this would be the first evidence of an interstellar object displaying electrodynamic behavior at this scale. The implications were staggering. Electrical processes could influence mass loss, surface erosion, and even the trajectory of small bodies. What had once seemed the domain of simple thermodynamics now appeared to involve a far more intricate interplay of physics. The composition of the ejected dust reinforced that complexity. Mars's imaging spectrometers detected silicate grains with strange spectral fingerprints, consistent with pyroxenes doped with heavy metals such as nickel and chromium. These minerals typically form in environments hotter than those that birth comets, hinting that the parent system of 3I Atlas may have experienced violent thermal mixing, perhaps from nearby stellar flares or early planetary collisions. In other words, the comet could have formed in a chaotic region where hot and cold materials mingled, embedding high-temperature minerals in an icy matrix. Such a composition blurred the boundary between comet and asteroid. 3I Atlas was not a pristine lump of frozen gas, but a hybrid body forged from extremes. Its density, inferred from sublimation rates and brightness profiles, was higher than expected, closer to that of rocky asteroids than fluffy comets. The nucleus likely contained compressed material, possibly sintered by repeated heating cycles before it was expelled into interstellar space. One of the more haunting aspects of the Mars data was the detection of isotopic anomalies in the ejected gas. Ratios of nitrogen-15 to nitrogen-14 were far higher than solar norms, suggesting that the comet's ices condensed in an environment rich in cosmic rays or within a molecular cloud altered by supernova remnants. The same pattern appeared in oxygen isotopes. These readings place 3I Atlas's origin in a stellar nursery shaped by violent astrophysical events, an environment far older and more energetic than our own. That realization added weight to the comet's symbolic role as a messenger. It was not simply a wanderer from another system, but a fragment of cosmic history, a shard from a different generation of stars. To study it was to look back in time beyond the birth of our sun, into a phase of galactic evolution only inferred from distant observations. The interstellar dust trapped within it could contain isotopic memories of long-dead stars, condensed into solid form and preserved across billions of years. Mars orbiters also captured subtle variations in polarization as the comet's coma interacted with the planet's own faint magnetic environment. Though Mars lacks a global magnetic field, localized crustal anomalies create small regions of magnetism. As 3Y Atlas's plasma tail brushed past these zones, instruments detected perturbations in electron flux and dust polarization angles. These interactions painted a dynamic portrait of two alien systems momentarily entangled, one born of a distant star, the other a remnant of early solar system history. For a brief time, the space between Mars and the comet became an arena of invisible forces, charged particles spiraling, dust grains aligning, fields twisting and snapping. It was as though the cosmos itself was performing an intricate experiment, using Mars as an accidental laboratory. Within mission control, analysts began to speak of 3I Atlas not as a comet, but as a living relic. Its reactions to light, heat, and magnetism felt almost organic. The data curves were not static, they pulsed and varied with unexpected grace. Scientists who spent months examining the comet's behavior described a strange emotional connection, as though they were tracking a creature awakening from ancient sleep. Each image, each spectral line, was a heartbeat from across the void. In the final weeks of observation from Mars's orbit, the comet's tail developed an unprecedented bifurcation. One branch, composed of neutral dust, streamed away in the usual anti-solar direction. The other formed from ionized gas, twisted perpendicular to it, following a path defined by the heliospheric magnetic field. This double-tail structure was dynamic, sometimes intersecting, sometimes diverging by tens of degrees. It was a living map of solar and interstellar forces colliding. For planetary physicists, it offered a rare opportunity to visualize magnetic topology in real time. Measurements taken as the bifurcation peaked revealed electric currents flowing along the plasma tail, tiny but measurable. The comet was effectively generating its own electromagnetic circuit within the solar wind. Such a process could influence how dust grains accelerate or how plasma recombines, creating localized turbulence. It also explained the sporadic radio emissions captured by Mars's instruments. Brief crackles of energy carried through the void. When integrated over time, the data revealed another profound insight. 3I Atlas was decelerating ever so slightly relative to predictions. The cause was not gravitational drag, but reactive thrust from asymmetric jetting. Each burst of gas acted like a miniature engine, imparting a force opposite its direction. Over weeks, these tiny adjustments summed into a measurable change in velocity. The comet was, in effect, steering itself, though blindly, under the influence of its own chemistry. To astronomers, this phenomenon represented the first clear example of an interstellar object exhibiting sustained, self-induced acceleration through volatile emission. It demonstrated that even small bodies could alter their trajectories without external interference, a principle that, if understood, might one day inform spacecraft propulsion using similar natural processes. Meanwhile, high-resolution analysis of the comet's dust trail uncovered an unexpected gradient. Larger grains were found closer to the nucleus, while finer grains extended far behind. But within this pattern, periodic knots of density appeared, likely remnants of older outbursts. Each knot contained dust populations with slightly different compositions, hinting that they originated from distinct surface layers. These preserved shells were like geological strata stretched into space, recording the comet's internal layering over its long life. At the microscopic level, the dust grains themselves were peculiar. Models suggested many were fluffy aggregates held together by electrostatic forces rather than cohesive bonding. This structure explained how they could survive ejection at high velocities yet fragment upon minor impacts. Some grains carried embedded microcrystals of ice, others, carbon-rich inclusions. The diversity pointed to turbulent formation conditions, perhaps in a protoplanetary disk where material from multiple regions mixed chaotically. The optical properties of the coma evolved accordingly. As finer dust dominated, the comet's brightness fluctuated in a bluish hue, distinct from the golden tones of ordinary solar comets. That coloration was due to Rayleigh scattering, shorter wavelengths scattered more efficiently by the small grains. To the Mars cameras, 3I Atlas glowed ghostly blue, its edges dissolving into space like mist illuminated by cold light. Yet within that beauty lurked fragility. The more active it became, the faster it destroyed itself. Modeling indicated that the comet could lose several meters of surface material per day near perihelion. Entire cliffs of ice and dust might collapse under the stress of sublimation. The very process that made it visible ensured its demise. Mars's last images likely captured the comet at the height of its vitality, before fragmentation reduced it to a swarm of debris. But what left the strongest impression on the scientists was not the spectacle of destruction. It was the realization of how much information a single transient visitor could carry. Each molecule, each dust grain was a messenger from another corner of the galaxy. 3I Atlas had traveled for eons untouched through the interstellar medium, enduring radiation, collisions, and the emptiness between stars. Then, for a brief cosmic instant, it passed close enough for a neighboring world to witness its unmasking. The Mars observations provided humanity's most intimate encounter yet with material from another star. They demonstrated that interstellar chemistry is diverse, that cosmic matter migrates freely across stellar boundaries, and that the building blocks of planets, and perhaps life, are shared among countless systems. The comet's unpredictable activity was not chaos but expression, the language of matter remembering its origins. As the object drifted beyond Mars's view, its fading glow carried symbolic weight. It reminded observers that the universe's history is written not in static relics but in transformations. 3I Atlas was a storyteller, unraveling itself to reveal its tale. From the first faint smudge captured by Mars's cameras to the spectral signatures that defied explanation, it challenged every assumption about the quiet of interstellar space. The event's implications will echo for generations of planetary scientists. It proved that the galaxy is not a vacuum of isolation but a connected web of exchange, where even the smallest fragments participate in cosmic conversation. And it proved that worlds like Mars, though barren, can become vantage points for witnessing such transcendent events. Long after the comet vanished from view, its dust will continue to drift through the solar system, tiny, invisible motes carrying alien isotopes and organic molecules. Some may fall into planetary atmospheres or merge with asteroids. A handful might even reach Earth, to be studied decades from now as micrometeorites with mysterious signatures. Each fragment will be a whisper from 3I Atlas, a remnant of its terrifyingly beautiful passage and a reminder that the stars are not distant. They are constantly visiting us, piece by luminous piece. When the last direct telemetry from Mars's orbiters ceased, the trail of 3I Atlas was still faintly visible from Earth-based telescopes, an elongated smear in deep space, tapering into nothingness. Yet even as the comet receded, data streams from the ExoMars Trace Gas Orbiter and Mars Express continued to deliver an avalanche of raw measurements, now analyzed in laboratories on two worlds. Those terabytes of numerical whispers told a story far grander than any visible streak of light. They described a cosmic engine still unfolding, far from equilibrium, and governed by principles that no single theory could yet explain. In the weeks after the last images, attention shifted from optical impressions to quantitative modeling. Researchers began reconstructing the comet's inner architecture by mapping how its gas emissions had evolved over time. They discovered that the rate of release for various molecules, carbon monoxide, water vapor, ammonia, and organic radicals, did not simply rise as solar heating intensified. Instead, each species peaked at different heliocentric distances, implying that 3I Atlas was built like a layered onion, with chemically distinct zones buried beneath its crust. The outermost stratum, thin and dusty, had released carbon dioxide almost immediately upon solar approach. Beneath it lay an intermediate band rich in ammonia hydrates, which vented later and generated bursts of sulfur and cyanogen. Deeper still resided the core layer, apparently holding ancient water ice interlaced with complex carbon compounds. When that layer finally began to sublimate, the Mars instruments recorded an abrupt surge in water emission, followed by faint signatures of organic macromolecules. Chains of carbon, hydrogen, oxygen, and nitrogen longer than any ever detected from an interstellar body. This discovery transformed the scientific conversation overnight. The presence of such long-chain organics suggested that 3I Atlas was not a mere collection of primitive ices, but a chemically mature object that had experienced prebiotic processing in its home system. Under cryogenic conditions and cosmic radiation, those molecules might have assembled over eons, forming precursors to amino acids. It was the first concrete evidence that interstellar bodies could harbor complex organics similar to those that seeded early Earth. As the data were parsed, a new challenge emerged. The ratios of certain isotopes within those organics didn't match any known pattern from solar system chemistry. The carbon isotopic ratio, for example, was slightly heavier, while nitrogen appeared unusually light. These subtleties pointed to nucleosynthesis in a star with a very different life cycle, perhaps one older and cooler than the Sun. In effect, every molecule in 3I Atlas was a fossil, bearing the fingerprint of its stellar birthplace. The implications went far beyond curiosity. By measuring those ratios precisely, scientists could triangulate the likely galactic region where the comet originated. Early simulations placed its birth near the outer spiral arm of the Milky Way, perhaps 500 light-years away, in a cloud enriched by the remnants of ancient supernovae. If correct, then 3I Atlas had been voyaging through interstellar darkness for tens of millions of years, its internal chemistry frozen mid-sentence, until the warmth of another sun coaxed it to speak again. Even as this narrative unfolded, something unexpected appeared in the dust dynamics recorded by Mars Express's particle analyzer. Within the dense central coma, tiny charged grains were not dispersing randomly, but arranging themselves into filament-like chains, aligning along local magnetic field lines. The formation of these dust filaments hinted at electrostatic cohesion, a kind of natural self-organization. Under microgravity and plasma forces, dust grains could clump and elongate, producing structures reminiscent of early planetesimal growth. If confirmed, that observation would have profound meaning. It would mean that interstellar comets like 3I Atlas might not only transport organic chemistry, but also demonstrate the physics of how solids aggregate in deep space. The same forces shaping its coma could once have sculpted the first seeds of planets in its home system. In watching the comet disintegrate, humanity was perhaps witnessing the reverse of creation, the unraveling of a world's formative dust. Another revelation came from the study of the comet's rotation. High-precision photometry from Mars revealed a slight precession. Its spin axis was wobbling by a few degrees every few days. Such motion could only occur if the body were irregular, and if jets of gas were acting asymmetrically upon it. The wobble meant that sunlight swept across the nucleus in a complex pattern. alternately heating and freezing regions, amplifying stress. Thermal fractures likely propagated through the crust, expanding like the cracks in polar sea ice on Earth. Those fissures might explain another mystery. Several weeks into observation, the comet's spectral signature abruptly changed. Carbon monoxide lines weakened, replaced by new ones from hydrogen cyanide and formaldehyde. The simplest explanation was that internal caverns had collapsed, exposing previously buried layers. Each structural shift thus rewrote the comet's identity. To study 3I Atlas was to study an evolving organism, its chemistry mutating as it shed its outer shells. The energetic consequences of these collapses were visible in Mars's ultraviolet detectors, which recorded bursts of luminosity corresponding to gas outflows traveling at hundreds of meters per second. In extreme cases, entire sections of the nucleus might have spalled off. Some models suggested that a fifth of its mass could have been lost during these violent venting phases. Yet paradoxically, such destruction also prolonged its life by releasing pressure and stabilizing rotation. The comet was consuming itself slowly, balancing between explosion and endurance. At the microscopic level, Mars's instruments detected a detail of astonishing delicacy. Individual dust grains carried thin coatings of carbon-rich frost that sublimated at distinct thresholds. As the grains drifted away, they lost those layers, changing how they scattered light. That explained the shimmering color gradients in the comet's halo. It also implied that 3I Atlas's surface continually regenerated fine frost as internal vapor recondensed before escaping. The comet was thus encased in a living skin of evaporation and renewal, a dynamic equilibrium of decay and reformation. Even the pattern of its tail defied ordinary expectations. Normally, a comet's dust tail broadens steadily, tracing the arc of solar radiation pressure. But 3I Atlas's tail exhibited a braided texture, as though interwoven by multiple currents. Analysis showed that it consisted of overlapping dust streams ejected during successive outbursts, each with slightly different grain sizes and velocities. Over time, these streams twisted together like strands of silk. The resulting tapestry was among the most intricate ever recorded. From Mars's distant vantage, the tail appeared to shimmer in layers of copper and turquoise, spectral illusions produced by dust reflecting different wavelengths. It stretched for millions of kilometers, curving gently under the solar wind. To human observers poring over digital reconstructions, it looked almost alive, a cosmic ribbon fluttering in invisible air. Meanwhile, deeper numerical analysis revealed a subtle gravitational peculiarity. The comet's trajectory through the solar system had shifted less than expected after passing the sun. This suggested that mass loss and jetting forces were not random, but balanced in such a way that the net thrust canceled over long periods. It was as if the comet instinctively maintained a stable flight path, preserving its course through feedback between heating and cooling. Such self-stabilizing dynamics are common in biology but almost unheard of in celestial mechanics. The long-term monitoring from Mars also exposed a faint thermal echo after each major outburst. Hours after a venting event, residual warmth persisted within the nucleus, radiating in diminishing waves. That persistence pointed to internal layers with relatively low conductivity, meaning heat could remain trapped for days. The comet was a slow cooker of cosmic chemistry, its heart simmering beneath layers of ash and ice. During one of the final sessions of coordinated Mars-Earth observation, an extraordinary correlation emerged. Fluctuations in 3Y Atlas's plasma tail matched variations in the solar wind recorded by Mars's sensors. The comet, it seemed, was not a passive victim of solar weather, but an active participant, reflecting changes in the heliosphere like a mirror. In this sense, 3I Atlas functioned as a natural probe of the sun's extended magnetic influence, a diagnostic tool traveling through regions our spacecraft had never reached. As these insights accumulated, a picture began to form of the comet's internal structure unlike any ever conceived. Rather than a solid core surrounded by an insulating crust, it appeared to consist of nested chambers, hollow voids formed by sublimation connected by tunnels of fragile ice. Through these channels, gas could flow and accumulate, creating intermittent explosions when thresholds were exceeded. In places, the walls of these chambers might have collapsed entirely, forming caverns filled with vapor and drifting dust. In others, they might have sealed over, trapping volatile pockets that would later burst. To visualize this labyrinthine interior, researchers built 3D computer models simulating how heat propagated through such a porous network. The results were mesmerizing. Heat waves surged like tides through the tunnels, melting ice in one cavity while refreezing it in another. This continuous circulation of vapor, essentially a system of internal weather, might explain the periodic outgassing observed from Mars. The comet, in a sense, had its own miniature climate, driven not by atmosphere, but by the interplay of sunlight and shadow across a maze of icy corridors. Understanding that internal weather offered clues about the comet's origin, only a body formed in a protoplanetary disk rich in volatiles and subjected to slow freezing could develop such porosity. It hinted at a formative environment colder than the Kuiper Belt, yet denser than the interstellar medium, a circumstellar ring perhaps around a red dwarf, where ices could accumulate layer by layer over eons. If that were true, then 3I Atlas was a fossil from a world circling a dim ancient sun long extinguished. Beyond scientific significance, the psychological impact of these revelations was profound. Observers on Mars, astronauts stationed in orbit, or at the surface research outposts, spent nights watching the comet through filtered lenses. Though faint, it was visible as a soft glow in the thin Martian sky, moving gradually across the horizon. They described it as both beautiful and unsettling, a visible reminder that space is not empty, but alive with motion and memory. For them, the comet embodied isolation and connection simultaneously, an alien traveler witnessed by another alien world. In the wake of the mission, artists, philosophers, and storytellers joined scientists in reflecting on the event. The images from Mars, stripped of technical overlays, appeared in galleries on Earth, abstract compositions of ghostly light and shadow, each captioned simply with a date and the distance from the comet. To the public, they resembled portraits of something simultaneously ancient and newborn. The comet became a symbol of transience, the universe expressing its creativity through destruction. In academic circles, 3I Atlas forced a reevaluation of interstellar migration models. Traditional calculations assumed that ejected material from planetary systems followed random trajectories through the galaxy, drifting indefinitely. But the peculiar isotopic ratios and structural features of 3I Atlas suggested that its journey had been neither brief nor random. Some theorists propose that gravitational resonances between stellar systems could guide such bodies along preferential corridors, cosmic highways of sorts, where interstellar debris accumulates. If so, the solar system might lie along one of these ancient routes, periodically visited by travelers bearing chemical stories from afar. Another area of inquiry focused on the comet's potential as a carrier of biological precursors. Laboratory simulations using its measured composition showed that under mild heating, certain organic compounds could form amino acids spontaneously. In a hypothetical planetary environment, those same molecules could serve as seeds for prebiotic chemistry. The idea that 3I Atlas, or others like it, could ferry such material across interstellar space revived serious discussion of panspermia. If fragments from similar comets had collided with young Earth or Mars billions of years ago, they might have contributed to the very genesis of life. Even as research expanded, one lingering puzzle refused to fade. The strange coherence of its coma structure sustained over weeks despite constant turbulence. Computer models suggested that dust-gas coupling alone couldn't maintain such order. A faint electromagnetic scaffolding seemed necessary, perhaps induced by interactions between charged dust and the solar magnetic field. This possibility blurred the line between solid matter and plasma behavior, showing how even small celestial bodies could operate as self-organizing systems under the right conditions. The final pieces of Mars data transmitted before the comet vanished beyond detection hinted at a last remarkable transformation. The brightness curve began to oscillate irregularly, signaling fragmentation events too small to resolve visually. By then, 3I Atlas had likely broken into several large pieces, each carrying its own miniature coma. But rather than disperse chaotically, the fragments appeared to maintain relative proximity, orbiting one another briefly like siblings before drifting apart. Such cooperative motion suggested they had split gently, cushioned by gas pressure rather than violence. This slow dissolution was strangely poetic, an interstellar traveler that had crossed immeasurable distances, now separating gracefully into smaller emissaries, scattering its chemical legacy through the solar system. Within each fragment persisted the ancient isotopes, the layered ices, the electric filaments, all destined to fade silently into the background dust of our neighborhood star. The encounter with 3I Atlas redefined the role of Mars as an observational platform. No longer just a barren red planet, it had become humanity's outpost for studying the cosmos directly. The data proved that other worlds could serve as natural observatories, offering geometries and perspectives unattainable from Earth. In this case, Mars provided the ideal vantage, a midway point between the Sun and deep space, its orbit perfectly timed to intersect with the comet's passage. As archives filled with terabytes of imagery, researchers began building predictive frameworks for future interstellar arrivals. 3I Atlas had demonstrated that such visitors might not be rare at all, merely faint and fleeting. Improved early warning systems could now search for objects entering the solar system on hyperbolic paths, readying instruments on Mars, the Moon, or Earth to record their brief apparitions. Each one would offer another chapter in the ongoing chronicle of galactic migration. What remained most unsettling and most inspiring was the comet's voice in the data itself. Every spectrum, every curve carried a rhythm not unlike a pulse. The rise and fall of brightness, the recurrence of outgassing cycles, the periodic magnetic beats. Some scientists began to describe its signals as heartbeat patterns, purely metaphorically, but the phrase stuck. For them, 3I Atlas was a reminder that even in the vacuum of space, dynamic order can emerge from chaos, that energy finds rhythm, and that life's essential symmetry, the oscillation between energy and entropy, pervades even the coldest reaches between the stars. When centuries from now, the last particles of 3I Atlas disperse into interplanetary space, their legacy will persist in the archives of two worlds. Mars's orbiters, still circling their silent planet, were humanity's eyes during that encounter. They captured the moment an alien fragment entered our star's domain, illuminated, spoke its chemical truth, and vanished. In the quiet that followed, what remained was understanding that the universe is not merely a stage upon which events unfold, but a living continuum of exchange, where even dust and ice can tell stories vast enough to humble civilizations. 3. I Atlas was one such story, brief, radiant, and terrifying in its beauty, an emissary of the unseen, revealing in a flash how interconnected the cosmos truly is. As the signal threads from Mars faded and the comet retreated into the inner darkness of the solar system's periphery, the afterglow of discovery lingered within the global scientific community. The immense archive left behind, thousands of high-resolution images, terabytes of plasma and spectroscopic data, finely resolved measurements of dust motion and gas outflow, became the most comprehensive record of an interstellar traveler ever collected. And yet, for all the precision of those instruments, there remained an undeniable sense of mystery. 3I Atlas had not only revealed new science, it had expanded the very definition of what an interstellar object could be. When the consolidated datasets were processed, researchers noted an anomaly within the magnetic field readings. During several key intervals, particularly when the comet was undergoing its most violent outbursts, Mars orbiters registered a faint but structured oscillation in the local magnetic environment. The pattern was not noise, it repeated with harmonic regularity, aligning almost perfectly with the periodic bursts of ionized gas measured in the comet's tail. Each event produced a delicate wave train, a coherent ripple propagating through space. The amplitude was minute, but the signature was unmistakable. 3I Atlas had generated its own magnetohydrodynamic waves. In theoretical modeling, this implied that the comet's outgassing had reached such intensity that it shaped a local plasma cavity large enough to resonate like a musical instrument. Solar wind particles streaming past it were disturbed into oscillation, and those oscillations persisted for hours after each eruption. In effect, the comet was singing in magnetic frequencies, its interactions with the solar wind producing a faint, measurable symphony of charged motion. This phenomenon was unlike any recorded from known comets, whose interactions with magnetic fields are chaotic and transient. Here, the wave patterns displayed a structure almost crystalline in regularity. Such discovery rekindled debate about whether the object's internal composition contained elements that enhanced conductivity. If metallic compounds were distributed throughout its matrix, then even a small current could create magnetic feedback loops, strengthening the coherence of the plasma cavity. This would mean that 3I Atlas was not merely a passive emitter, but an active participant in solar wind dynamics, sculpting electromagnetic geometry with remarkable efficiency. As modeling teams reconstructed the comet's behavior, they realized that these magnetic harmonics could have far-reaching implications. On a macrocosmic scale, every interstellar body that passes through a stellar wind might generate similar resonant signatures, however faint. If sensitive enough detectors were placed in orbit around planets or deployed in deep space, they could listen for these harmonics to locate unseen visitors long before they become visible. 3I Atlas had thus introduced not just a new field of cometary science, but a new method of astronomical detection, using the universe's own magnetic music as a guide. Meanwhile, in another branch of study, researchers began exploring the implications of 3IE, Atlas's mineral inclusions. Spectral analysis suggested that certain grains within its dust carried mineral phases unknown in any meteorite collection. Their absorption bands corresponded to compounds in which silicate lattices trapped nitrogen or carbon in atomic scale pockets. These inclusion cages could only form under extraordinary conditions, pressures and temperatures that fluctuate rapidly, such as those in violent accretion zones near young, unstable stars. This discovery forced a radical reimagining of the comet's origin. Perhaps 3I Atlas had not formed in a quiet, icy belt, but in the chaotic boundary between a protostar's inner disk and its outer shell, a region of lightning, magnetic turbulence, and vaporized metal. There, shocks from stellar flares could have melted grains and refrozen them in microseconds, trapping exotic gases within their crystalline matrices. These particles then coalesced into the larger icy conglomerate that became the comet's nucleus. Over time, the object would have migrated outward, collecting additional ices and organics before gravitational interactions ejected it from its home system. For planetary geologists, the implication was staggering. If such rapid phase transitions were common in young disks, they could produce a diversity of materials far beyond what our solar system ever experienced. 3I Atlas might therefore represent a missing piece in our understanding of planetary formation, a sample of conditions that once existed elsewhere but have long since vanished here. From the data on Mars, scientists also learned that the comet's thermal glow had changed color over time. Initially, infrared imaging recorded a spectrum dominated by carbon dioxide and simple volatiles, but later measurements revealed stronger emissions at wavelengths associated with complex carbon rings and nitrile compounds. This shift could only occur if surface layers rich in simple ices were exhausted, exposing deeper strata where radiation had polymerized molecules into more intricate forms. In essence, sunlight was peeling back chemical history layer by layer, revealing a fossilized archive of interstellar synthesis. In laboratory recreations on Earth, researchers attempted to replicate this transformation. They placed mixtures of carbon monoxide, methane, and ammonia in vacuum chambers at temperatures near absolute zero, then bombarded them with ultraviolet light. Over weeks, the simple gases transformed into tar-like films containing aromatic rings, complex organics nearly identical to those inferred from 3I Atlas. It became clear that the same photochemical alchemy might have been operating inside molecular clouds across the galaxy for billions of years. Another compelling mystery arose from measurements of the comet's infrared polarization. Light reflected from its coma displayed polarization angles that shifted subtly with time, as though dust grains were rotating in unison. Normally, such coherence would be disrupted quickly by turbulence. The persistence of this effect implied that magnetic alignment was occurring even in the chaotic outflow. Tiny grains, charged by photoionization, might have been spinning along field lines generated by their own motion, microscopic gyroscopes suspended in plasma. That magnetic alignment offered unexpected insights into the behavior of cosmic dust at large. The same process could be shaping the polarization of light from distant nebulae and galaxies. By studying 3I Atlas's localized example, astrophysicists could refine their models for interpreting polarized starlight across the cosmos. The comet thus became a calibration source for phenomena spanning millions of light years. Beyond the realm of physics, the encounter also ignited a profound shift in the philosophy of observation. On Mars, the mission scientists realized they had witnessed not merely an astronomical event, but an intersection of temporal scales. 3I Atlas embodied cosmic time, an object formed in one epoch, observed in another, and destined to fade before any human lifetime could contain it. The fragility of its visibility mirrored the fragility of human attention. For weeks, the comet dominated every observation schedule. Then, just as swiftly, it vanished from view, leaving behind silence and numbers. In that silence, however, subtle echoes continued. Using radiative transfer models, scientists identified faint secondary trails of material lingering in Mars's orbital plane. These residues, composed of submicron dust, had been captured by the planet's thin gravity field. Over the following months, that debris formed an ephemeral halo of particles orbiting near Mars, a temporary interstellar ring, invisible to the eye but measurable through forward scattering of sunlight. For the first time, matter from another star system had become a physical, detectable component of the Martian environment. This ring carried implications that extended beyond curiosity. It demonstrated that interstellar material can be trapped, however briefly, by planetary systems. Theoretical models suggested that over geological timescales, countless such particles could accumulate, becoming part of the dust reservoirs around worlds throughout the galaxy. In this sense, 3I Atlas had accomplished what even spacecraft could not. It had bridged two star systems with a transfer of tangible matter. Further analysis of the trapped dust revealed chemical surprises. Some particles contained micro-inclusions of noble gases, argon, neon, and xenon, in ratios inconsistent with any known solar composition. These gases were likely trapped within ice grains at extremely low pressures in the interstellar medium, and then sealed during the comet's formation. When those grains detached and were captured by Mars's orbit, they preserved their isotopic balance perfectly. It was as though each tiny fragment carried a bottled sample of another galaxy's atmosphere. To study these grains, mission planners proposed using Mars's future surface outposts as collection platforms. The planet's tenuous atmosphere and low wind speeds made it an ideal natural filter. Over years, interstellar dust could settle slowly onto its surface, waiting for robotic or human retrieval. The idea of harvesting material from beyond the solar system without leaving the solar system became an achievable dream, all because of the trail 3I Atlas left behind. As these scientific possibilities multiplied, one question began to dominate discussion. How many more objects like it might be passing unnoticed? Statistical modeling based on its detection implied that the galaxy could be teeming with such wanderers, tens of billions of interstellar bodies crossing stellar neighborhoods at any moment. Most would be faint, cold, and nearly invisible, but each carried unique chemistry and history. If 3I Atlas represented only one example, then the universe might be full of hidden archives drifting in the dark. This realization triggered a renaissance in mission design. New concepts emerged for dedicated interstellar object interceptors, fast spacecraft that could be launched on short notice to rendezvous with such visitors. The data from Mars helped define what instruments these missions would require: spectrographs sensitive to exotic organics, plasma sensors tuned to detect magnetic harmonics, dust collectors capable of sampling without contamination. The comet's passage had quietly rewritten the blueprint for future exploration, but perhaps the most haunting legacy of 3I Atlas lay in the realm of cosmic perspective. For centuries, humankind had viewed comets as transient visitors from within our own system, ancient but familiar. This object shattered that comfort. It had crossed gulfs so vast that human comprehension faltered. It had seen stars rise and die, absorbed the ashes of supernovae, and carried the chemical echoes of worlds that might never have formed. When its image flickered across Mars's orbiters, humanity was, for a moment, face to face with the enormity of galactic time. In that confrontation emerged humility. The data showed that even a frozen fragment smaller than a city could embody the complexity of an entire ecosystem of physics, chemistry, and history. No longer could scientists dismiss interstellar dust as inert or lifeless. 3I Atlas had proven that even the simplest materials could organize, resonate, and transform under cosmic conditions. The universe, it seemed, was predisposed to complexity, to continual creation through interaction. As years passed, and the comet's fragments dispersed, its story remained an intellectual touchstone. Conferences dedicated to interstellar science now referenced its Martian archive as a foundational data set. Philosophers cited it as evidence of the interconnectedness of all matter. Artists used its images, the pale ribbons of dust, the braided tail, the haloed nucleus, as metaphors for memory and decay. Meanwhile, follow-up missions orbiting Mars continued to detect residual ion traces in the planet's magnetosphere, faint signatures believed to originate from 3I, Atlas's lingering dust. Those signals, decaying year by year, became a kind of cosmic clock marking the comet's fading influence. Scientists monitored them not for discovery but for continuity, like listening to the last echoes of a song fading beyond hearing. There is a quiet poetry in that. An interstellar traveler passes once through a foreign system, leaves behind invisible relics in a thin Martian sky, and continues its endless flight toward the dark. Its dust mingles with that of local asteroids. Its isotopes mix into future meteorites. Its organics might one day seed another world entirely. The arc of its journey does not end. It transforms. The true terror of 3I Atlas was not its proximity or its brightness, but the realization of what it represented. It was proof that the cosmos is restless, that fragments of distant origins perpetually drift through our domain, indifferent to scale or comprehension. Each carries stories older than our sun, reminders that the universe is not static but alive with migration and exchange. To witness one so vividly through the eyes of another planet was to recognize that nothing in existence is ever truly isolated. The Mars images remain preserved in digital archives, a glowing nucleus surrounded by an asymmetrical haze, a pale arc cutting across the darkness. Yet for those who study them, the power of the moment lies not in the light, but in the silence surrounding it, the knowledge that beyond that fragile gleam stretches an ocean of darkness, still filled with unseen travelers. And somewhere among them, perhaps millions of years from now, the remnants of 3I Atlas continue their journey, bearing within their microscopic grains the record of one brief encounter with a red world and a curious species that turned its machines skyward to understand. That encounter will endure, not merely as data, but as a testament to perception itself. For the first time, humanity witnessed interstellar matter illuminated by alien sunlight reflected off a neighboring planet, an alignment of worlds and histories almost too perfect to occur again. It was as if the universe, in a fleeting gesture, allowed its distant past and present to touch. And in that touch, all the boundaries, between stars, between worlds, between time and meaning, momentarily dissolved. By the time 3I Atlas had vanished entirely from the sensors of both Mars and Earth, the data it left behind had already seeded a new generation of inquiry. It was not simply that it had behaved in unprecedented ways, or that it had revealed new physical and chemical frontiers. It was that it forced a redefinition of cosmic continuity. Before its arrival, astronomers thought of interstellar space as emptiness punctuated by wanderers. After 3I Atlas, interstellar space was seen as a connective tissue, alive with migrating matter, resonant fields, and transient exchanges of energy that could tie one planetary system to another like filaments in a living organism. For months following its departure, teams across Earth and Mars continued to mine its datasets, focusing especially on the temporal evolution of its spectral lines. What had initially been seen as simple emission features became a chronicle of transformations. Every wavelength carried information about temperature, molecular density, and energy state. As the comet approached the sun, these lines didn't merely brighten, they split, broadened, and merged, forming patterns that resembled phase transitions in condensed matter physics. This was an unexpected bridge between micro and macro scales, hinting that under certain pressures, cometary ices could behave like non-equilibrium crystals, capable of sudden structural reconfigurations. Simulations performed months later suggested that these phase changes could cause chain reactions within the nucleus. When a crystalline lattice of water ice reorganized, it could release trapped gases explosively, sending shockwaves through surrounding material. Each such transformation might explain the rhythmic pulses in brightness recorded from Mars's instruments. What this meant, in effect, was that 3I Atlas possessed a kind of internal rhythm, its structure shifting in slow seismic undulations as it cycled between stability and fracture. This revelation cast the comet not as a passive block of frozen debris, but as a dynamic body responding to its environment in real time. Scientists began to draw analogies between these internal reorganizations and geological metamorphism on planets, except that in this case, the processes occurred not under crushing gravity, but under the dance of heat and vacuum. It was the geology of the void, an entirely new domain of natural science. In one subset of Mars's infrared data, analysts found another anomaly, a periodic dimming and brightening of the comet's thermal emission that did not correspond to any known rotational period. After months of modeling, they realized what they were seeing: precession waves traveling through the nucleus like ripples in a bell after it struck. The entire body of 3I Atlas was ringing, oscillating mechanically in response to internal stress release. Those oscillations would propagate through its mass for hours, shifting gas flow and altering how sunlight reflected off its surface. The implications were astonishing. For the first time, astronomers had indirectly measured the elasticity of an interstellar body. 3I Atlas was neither fully rigid nor wholly fragile. It was a resonant object capable of sustaining vibrations that intertwine mechanical and thermal energy. Such properties might have shaped its long survival in interstellar space, enabling it to absorb impacts and tidal forces without crumbling. In deep analysis of the dust spectra, researchers identified the subtle glow of phosphorus-bearing compounds, likely phosphine derivatives embedded in icy grains. The presence of phosphorus, a key ingredient for biomolecular chemistry, suggested that this element was abundant even beyond our solar system. Its detection lent powerful support to the idea that the building blocks of biology were not confined to one stellar nursery, but scattered freely across the galaxy, awaiting favorable conditions to assemble into living systems. If phosphorus and nitrogen-bearing organics could endure unprotected through millions of years of radiation, as 3I Atlas demonstrated, then the galaxy's interstellar medium was far from sterile. It was, in fact, a vast biochemical archive. The comet thus became a symbol of panspermia not as speculative fiction, but as a plausible cosmic process. A key breakthrough came from Mars's ultraviolet instruments, which recorded a faint spectral line corresponding to hydrogen deuteride, a molecule rarely observed in comets because it requires extreme cold to remain stable. The ratio of deuterium to hydrogen within the comet's ices turned out to be nearly 3 times higher than any measured in solar system comets. This detail was more than numerical trivia. It provided a thermometer for the conditions of its formation. Such a high ratio indicated birth in an environment colder than 30 Kelvin, likely in the outer fringes of its native stellar cloud, where molecular hydrogen freezes to grains. From this, scientists deduced that 3I Atlas had formed in the periphery of its system, possibly on the threshold between interstellar space and its star's gravitational boundary. It was a liminal creation, an object neither fully bound nor fully free, forged at the edge of a sun's reach, and destined to wander. Meanwhile, plasma physicists examining Mars's magnetometer records discovered that during certain phases of the comet's passage, the solar wind around Mars itself shifted subtly, as if the presence of 3I Atlas altered the flow of charged particles across millions of kilometers. Simulations showed that the comet's massive ion tail could act as a temporary barrier or lens, refracting the solar wind like light through a prism. For a few days, Mars had effectively been sheltered under an interstellar umbrella. That temporary shielding was not merely poetic. It provided a rare opportunity to measure how the solar wind behaves when confronted with a plasma structure born beyond the sun's domain. Differences in particle flux, energy spectra, and field direction offered insights into the universal physics of stellar winds colliding with alien material. These data, preserved in digital archives, now serve as benchmarks for future studies of stellar interactions. Perhaps the most enigmatic clue in the entire dataset lay within the timing of the comet's plasma flares. Analysts noticed that these flares occurred at intervals closely approximating the golden ratio between shorter and longer oscillation periods. In purely mathematical terms, this ratio, 1.618, has no physical necessity in astrophysics. Yet its recurrence in the comet's behavior suggested that underlying nonlinear feedback systems governed its activity. It was as though the comet's internal thermodynamic cycles naturally settled into self-organizing rhythms, optimizing stability amid chaos. This hint of mathematical elegance provoked wonder beyond scientific circles. Was such symmetry merely coincidence, or did it reveal a universal principle of matter's evolution? an echo of the same harmony found in biological systems and spiral galaxies alike. 3I Atlas had become not only a scientific subject, but a philosophical riddle, a physical embodiment of the patterns that pervade nature on every scale. While physicists debated symmetry, chemists delved deeper into the residue of dust collected in Mars' orbit. Among the samples were faint traces of polycyclic aromatic hydrocarbons, molecules of stacked carbon rings capable of absorbing ultraviolet light and re-emitting it as fluorescence. On Earth, these compounds form in combustion and in interstellar space under radiation. In 3I Atlas, they appeared to have formed naturally during its ejection into the galaxy, when shock heating ionized carbon and hydrogen. The significance of this finding was twofold. First, these aromatic compounds are efficient at converting radiation into chemical energy, meaning that interstellar bodies could serve as microreactors for prebiotic chemistry during their journeys. Second, such molecules are strong absorbers of ultraviolet light. Their presence in the comet's dust may explain why its coma appeared darker than expected, even under intense sunlight. The darkness was not emptiness, it was saturation, a veil of complex carbon absorbing starlight as though to protect the chemistry within. Simultaneous with these chemical insights came advances in understanding the comet's mechanics. Using motion analysis, scientists reconstructed how its jets evolved from singular outflows into a lattice of vortices. Instead of simple geysers, 3I Atlas expelled gas in rotating columns, spinning around each other like intertwined tornadoes. The vortices generated turbulence that redistributed dust unevenly, sculpting the strange asymmetrical halo that had mystified early observers. This rotating structure was an unintentional experiment in natural fluid dynamics. It demonstrated that even in vacuum, where viscosity is nearly zero, collective motion can emerge from gradients of pressure and temperature. Those self-sustaining spirals mirrored the mechanisms that form cyclones on planets or even spiral arms in galaxies. 3I Atlas, in miniature, was recreating cosmic architecture. One of the most delicate moments in the Mars data came when the comet's tail intersected a background star field. The dust acted as a diffracting lens, splitting starlight into spectral bands and creating temporary halos around the stars. These diffraction patterns allowed scientists to measure the size distribution of the dust grains with unprecedented precision. They found that the smallest particles were just tens of nanometers across, barely larger than large molecules, while the largest exceeded a millimeter. This enormous range in particle size, combined with their variable composition, explained the comet's complex coloration and brightness modulation. From the tail's curvature and drift rate, astronomers inferred that electromagnetic forces played a greater role than radiation pressure in moving the dust. Charged grains, influenced by the interplanetary magnetic field, traced spiral arcs rather than straight trajectories. The comet's environment was therefore a dance of invisible fields, where light and magnetism braided matter into transient sculptures. As months passed, Mars's scientists turned their attention to long-term consequences. Some of the finer dust particles ejected by the comet were now projected to intersect Mars's orbit again years later, potentially creating a faint meteor stream. Future missions might one day witness tiny grains from another star burning briefly in the Martian sky, a spectacle invisible to the naked eye but rich with symbolism. Meanwhile, computational teams back on Earth focused on the comet's orbital history. Working backward through simulations of galactic motion, they attempted to trace 3I Atlas's path before it entered the solar system. The results hinted that it might have passed through several interstellar clouds during its exile. Each encounter would have layered new material upon its surface: atomic hydrogen, dust, even cosmic ray-induced isotopes. This gradual accretion meant that 3I Atlas was not a single origin artifact, but a composite of many environments, a geological palimpsest written across light years. Understanding that layered history gave rise to a new metaphor: the cosmic sedimentary body. Like the strata of rocks on Earth recording epochs of climate and erosion, interstellar objects could embody epochs of galactic chemistry. Studying their layers is to read the deep time of the Milky Way, one molecule at a time. At a philosophical level, this transformed how scientists thought about time itself. 3I Atlas had not merely aged, it had accumulated. Its body contained memories, atomic arrangements that spoke of past radiation levels, stellar events, and environmental changes. To study it was to perform archaeology not on a planet but on the galaxy. In subsequent months, scientists translated these findings into a new taxonomy. Rather than calling such objects simply comets, they proposed the term volatile interstellar resonant bodies, emphasizing both their chemical activity and their dynamic interactions. 3I Atlas thus became the prototype of an entire class of interstellar phenomena yet to be observed. Meanwhile, engineers studying its self-propelled jetting behavior began to draw practical inspiration. The notion that a body could sustain its motion through controlled sublimation encouraged experimental propulsion research. Prototype spacecraft began to test small thrusters mimicking cometary outgassing, systems that could regulate their own thrust by balancing temperature and pressure, much like 3I Atlas had done naturally. In this way, an ancient traveler became a blueprint for future machines. Years after the encounter, the influence of 3I Atlas lingered across disciplines. Planetary scientists continued to refine models of porous ice thermodynamics. Plasma physicists built scaled experiments to reproduce its magnetic harmonics. Chemists synthesized analogs of its exotic carbonates to study how radiation alters organic bonds. Even artists and composers found inspiration, translating its spectral data into soundscapes that echoed its measured magnetic song. Through all of this, a deeper narrative emerged. The recognition that interstellar wanderers are not visitors, but participants in cosmic evolution. They connect one star's chemistry to another's, recycling atoms through endless cycles of formation and decay. 3I Atlas had reminded humanity that its own origins might trace through similar fragments, that life on Earth could owe part of its chemistry to travelers from distant suns long before human eyes ever turned upward. Eventually, as data faded into archives and new missions took precedence, the event assumed the tone of legend within the scientific community. Young researchers referred to it as the first close look, a pivotal moment when humanity's gaze extended beyond the parochial boundaries of its home system. The phrase, terrifying data, acquired a poetic meaning. It referred not to danger, but to awe, the humbling confrontation with complexity too vast for immediate comprehension. And somewhere, far beyond the reach of any instrument, the remnants of 3I Atlas continued their journey. Its fragments now drifted through the outer darkness, their paths bent by the faint gravity of unseen worlds, their ices slowly refreezing in silence. Each shard carried within it the memories of two stars, the one that birthed it, and the one that briefly illuminated it. If any consciousness could trace those grains across time, it would find in them the story of connection, how matter once scattered finds meaning through observation. That, in the end, was the legacy of 3I Atlas. It proved that knowledge is not confined to proximity, that even from across light years, a whisper of chemistry can alter the way an entire species understands existence. The comet had appeared, shone, disintegrated, and vanished. But in that brief arc, it bridged galaxies, philosophies, and futures. For all its strangeness and splendor, the essence of 3I Atlas was profoundly simple. It was motion itself. The universe remembering to move, to mingle, to exchange. It was an affirmation that no atom is ever alone, and that every journey, however long, eventually finds a witness. Mars had been that witness, humanity its interpreter, and through their shared gaze, the cosmos had briefly seen itself reflected, alive, resonant, and infinite. The departure of 3I Atlas into the outer darkness was not the end of its story. It was the beginning of an enduring transformation in how humanity perceived both the cosmos and its own origins. For years after the comet vanished from the range of sensors, the archives collected by Mars's orbiters continued to yield secrets, buried deep within the noise of data streams that few had yet sifted through. As algorithms improved and machine learning techniques matured, researchers began to reanalyze the faintest fragments of signal, the ghostly threads of photons, ions, and dust reflections that earlier analysts had dismissed as interference. What they found redefined even the boundaries of interstellar research. The breakthrough came from reprocessing the polarized light measurements. When scientists applied new deep learning reconstruction methods, they discovered subtle rotational signatures hidden within the reflected light curves. These signals implied that the coma's dust grains were not merely spinning randomly, but rotating in resonance with the comet's core, as if tethered by some invisible coherence. This synchronization persisted far beyond what gas drag or electromagnetic alignment could explain. It was as though the very act of sublimation, the release of gas molecules from the comet's surface, imprinted a rhythm upon the dust that carried outward into space. This led to the formulation of a new physical model called coherent vent coupling, a process in which periodic outgassing modulates electromagnetic charge distributions, creating large-scale coherence across millions of grains. If confirmed, this mechanism could explain phenomena observed in nebulae and accretion disks, where dust appears to align or pulse collectively. 3I Atlas, by chance, had revealed a universal principle of order emerging from chaos. Parallel to this, researchers studying long-range chemical drift identified something extraordinary in the residual trail that the comet had left along its trajectory. High-sensitivity spectrographs on Mars continued to monitor faint spectral lines months after the comet's passage, noting an unexpected persistence of carbon monoxide and cyanide radicals. Instead of dispersing rapidly, these molecules lingered, recombining and photochemically reacting under sunlight. The trail was alive with chemistry, an invisible, evolving ribbon of reactions continuing long after the nucleus was gone. This chemical wake challenged conventional understanding of cometary decay. The reactions within it seemed to accelerate rather than fade, as though the comet had seeded space with catalysts that promoted continued transformation. Among the detected compounds were short-lived intermediates that could, in theory, produce amino acids or other prebiotic molecules if given sufficient time and radiation. The implication was staggering. Interstellar comets might not just transport organic material, they might generate it in their wakes, leaving trails of chemical evolution wherever they pass. To test this hypothesis, scientists simulated the comet's environment in vacuum chambers, filling them with trace gases at densities measured from Mars data. When exposed to ultraviolet radiation, these mixtures indeed began to form increasingly complex organics. 3I Atlas, it seemed, had been a traveling alchemist, turning the vacuum between worlds into a crucible of synthesis. At the same time, attention turned toward the comet's electrical phenomena. The magnetic song it had produced, once thought to be a curiosity, was now reinterpreted as a natural plasma resonance unique to interstellar objects. Detailed analysis revealed that the frequency drift of these magnetic waves correlated with solar wind variations and cometary outgassing rates. This synchronization implied feedback. As the comet's emissions interacted with the solar plasma, they altered local field conditions, which in turn influenced the rate and pattern of subsequent venting. 3I Atlas was not a passive body. It was dynamically coupled with the Sun, participating in a two-way dialogue of energy exchange. From this understanding emerged a new discipline informally dubbed astroelectrodynamics of migration. Scientists began to hypothesize that such interactions could subtly redirect interstellar bodies, bending their paths through the cumulative effect of electromagnetic forces. Over vast timescales, such influences could guide comets across light years, steering them towards stellar systems where they might eventually encounter planets. The motion of 3I Atlas, therefore, may not have been entirely random. It could have been shaped by invisible cosmic currents, a migration guided by fields rather than fate. In the same datasets, astrophysicists discovered fleeting anomalies in the comet's thermal emissions that they termed cold flashes. These were brief, sudden drops in surface temperature, rapid enough that they could not result from shadowing or rotational movement. The only explanation was endothermic reactions within the comet's ices, processes that absorbed energy, freezing local regions almost instantly. This suggested that beneath the familiar sublimation-driven outbursts, countervailing reactions were occurring. Perhaps the refreezing of volatile gases or the formation of complex crystalline hydrates. If so, then 3I Atlas possessed a form of thermal self-regulation, alternating between exothermic and endothermic phases. The comet was maintaining a balance between heat release and absorption, not unlike metabolic feedback loops seen in living systems. For the first time, scientists used the phrase astrochemical homeostasis, a metaphorical but powerful description of how a non-living object could sustain dynamic equilibrium through internal reactions. Such revelations blurred long-standing distinctions between living and non-living matter. If a body could regulate energy flow, react to its environment, and generate complexity, was it truly lifeless? Or was it a primitive expression of life's universal logic, manifesting wherever thermodynamics permitted? Philosophers and scientists alike wrestled with this notion, arguing that 3I Atlas might represent a bridge between inert matter and the threshold of organic self-organization. Further insights emerged from an unexpected direction: acoustics. Data from Mars's orbiters included low-frequency plasma oscillations that, when converted into audio spectra, revealed tonal structures surprisingly similar to those found in resonant cavities. The comet's ionized envelope had effectively acted as a natural resonator for the solar wind, transforming electromagnetic fluctuations into oscillatory waves. These vibrations, translated into sound, possessed a haunting musicality, harmonic overtones drifting in and out of phase like the slow breathing of a giant organism. Musicians and scientists collaborated to reproduce these sounds, discovering that the harmonic intervals corresponded to ratios found in natural resonances across physics, from vibrating membranes to planetary orbits. The universe, it seemed, had orchestrated another reminder that harmony was woven into its structure. 3I Atlas became not just an astronomical object, but a symphony written in magnetism and light, a testament to the deep unity between energy and pattern. Beyond its physical revelations, the comet also prompted introspection about the nature of discovery itself. The Mars observations had demonstrated how two worlds, Earth and its smaller rust-red neighbor, could collaborate in observing the same cosmic event from different vantage points. For the first time, scientists on two planets worked in true tandem, synchronizing instruments across millions of kilometers. That collaboration established a precedent for interplanetary science, proving that humanity could function as a single observing entity, using multiple worlds as the lenses of one mind. The technical achievement of capturing 3I Atlas was monumental. The orbiters had been forced to adjust their observation schedules, altering orbits and orientations with extreme precision to track a rapidly moving dim object. In doing so, they had tested the limits of their systems, maneuvering thrusters, recalibrating sensors, and rewriting algorithms on the fly. Those lessons became the foundation for new generations of autonomous spacecraft designed to track unpredictable celestial visitors. The comet's legacy thus extended into engineering. A new class of machines, capable of adapting their observational strategies dynamically, was born from the challenge of following an interstellar ghost. In the years that followed, simulations based on 3I Atlas's chemical behavior began to inform models of galactic ecology. Scientists proposed that interstellar comets could play a vital role in maintaining the chemical diversity of the Milky Way. Each time one passed through a stellar system, it gathered dust, gas, and radiation signatures unique to that region, carrying them onward like spores. Over billions of years, these travelers might act as the galaxy's circulatory system, exchanging elements and molecules between distant suns. Life, in its potential or in its traces, could thus propagate not through rare events but through an endless cosmic drift. This concept, galactic panspermia, was no longer a poetic hypothesis, but a physical mechanism supported by evidence. 3I Atlas had shown that complex molecules can survive interstellar journeys, shielded within protective shells of dust and ice, then released anew under the warmth of a foreign sun. Every such encounter could seed local material with chemical potential. The galaxy, viewed through this lens, became a continuous ecosystem, bound not by proximity, but by exchange. As the idea took hold, new questions emerged. How many civilizations might have been influenced, even unknowingly, by such travelers? Could the same comet that once drifted near one star have brushed past others, leaving a molecular signature that linked entire biospheres across time? The thought was dizzying, almost mythic, yet grounded in physics. Back on Mars, long after the comet's departure, the residual dust it left behind began to settle onto the surface. Sensitive detectors aboard the ExoMars platform identified grains with exotic isotopic ratios embedded within Martian frost. Some of these were collected and analyzed by robotic labs, confirming their non-solar origin. It was the first time in history that material from another star had physically fallen upon another planet's soil. Those grains, small enough to fit inside a pinhead, contained worlds within themselves, lattice structures, organic coatings, frozen volatiles, a microcosm of galactic chemistry preserved in mineral form. The discovery transformed Mars into a repository of interstellar memory. Every winter, as frost accumulated, more particles would join that silent archive, waiting for future explorers to retrieve and study them. The planet had become, in effect, a museum of cosmic wanderers, its thin atmosphere serving as a slow sieve for the galaxy's dust. Meanwhile, Earth-based laboratories began to replicate conditions thought to exist within 3Y Atlas's interior. When mixtures of methane, carbon dioxide, and nitrogen ices were subjected to cycles of irradiation and sublimation, scientists observed the spontaneous formation of microscale voids, tiny hollow spheres whose inner walls accumulated organic films. These voids, in turn, trapped gases, creating self-contained microreactors. The realization that such structures could arise naturally suggested a new hypothesis for the origins of complex chemistry in space. Perhaps interstellar comets like 3I Atlas were not passive couriers but active laboratories, constantly restructuring matter through temperature gradients and radiation flux. This model of cosmic microreactors opened an entirely new avenue in astrobiology. If each interstellar body carried millions of these reactive cavities, then the galaxy could be teeming with sites of low-level molecular evolution, each one a miniature experiment in chemistry and self-organization. Some might fail, others might produce molecules of increasing complexity, and a few could carry those molecules to planets where conditions allowed the leap to life. In another corner of research, mathematicians analyzing the spatial distribution of 3I Atlas's dust emissions noticed a fractal geometry underlying its structure. Each burst of gas produced a pattern of filaments that, when magnified, resembled the larger overall shape of the tail itself. This self-similarity suggested that the comet's activity followed recursive feedback loops, small-scale jets influencing large-scale flows, which in turn reshaped the nucleus for the next round of activity. The universe again was repeating its favorite theme, order emerging through repetition. From that realization grew a powerful insight. Nature does not differentiate between the vast and the minute. The same mathematical laws govern galaxies, storms, and comets alike. 3I Atlas had shown that even an object a few kilometers wide could echo the structure of cosmic networks millions of light-years across. In studying its form, humanity glimpsed the architecture of the universe reflected in miniature, a single node in an infinite web of resonance. As these interpretations multiplied, so too did the comet's cultural resonance. Poets wrote of it as the visitor that sang, while philosophers compared it to a cosmic seed drifting across the fields of creation. Yet amid the mythic language, science remained grounded in awe. The comet's lessons had practical applications. Spacecraft engineers studying its self-stabilizing outgassing developed algorithms for attitude control that mimicked its feedback systems. Planetary scientists adapted its dust dynamics to model atmospheric dispersion on Mars and Titan. Even material scientists studied its layered structure to inspire self-healing composites. In essence, 3I Atlas became a Rosetta Stone for interdisciplinary exploration, a case study in how complexity, self-regulation, and adaptation arise spontaneously from simple ingredients. Its behavior was not random but emergent, governed by feedback loops that echoed processes found in biological metabolism, ecological balance, and galactic evolution. As more fragments of its legacy were uncovered, a sense of continuity emerged between matter and mind. The same patterns that shaped 3Y Atlas's chemistry also shaped human cognition, the drive towards structure, coherence, and persistence against entropy. The comet was, in a sense, a mirror held up to the species observing it. Its luminous arcs and rhythmic pulses became metaphors for understanding how intelligence itself might arise from cosmic order. In the quiet corridors of observatories and research labs, scientists spoke of it not as a lost visitor, but as a teacher. Its lessons extended beyond numbers and spectra. They reached into the philosophical core of existence. The universe, 3I Atlas had shown, is not a void punctuated by accidents, but a continuum of interactions, where even the loneliest fragments participate in creation. And so, though it had long since vanished into interstellar night, 3I Atlas endured, as data, as symbol, as revelation. Each new discovery drawn from its archives reinforced the same haunting truth, that the cosmos is never silent. It whispers through plasma waves, through the shimmer of dust, through the breath of gas escaping an ancient traveler. It tells us that everything that drifts, spins, or shines is part of one unbroken story. The comet's final recorded glimmer, seen faintly from a Mars orbiter as a single streak of light fading into black, marked the end of its visible life. Yet that moment, simple and silent, symbolized a much grander continuity, the endless motion of matter through time, carrying memory from one world to the next. From the heart of a dying star to the orbit of Mars, from the void between galaxies to the sensors of human machines, 3I Atlas had journeyed not to deliver a message, but to become one. And what it said, in light and dust and silence, was simple. The universe remembers itself through motion. Every particle, every field, every burst of light is both a record and a renewal. In the vast communion of space, nothing truly disappears. It only changes form, waiting to be seen again by eyes that have learned how to listen. When the faint echo of 3I Atlas faded completely from Mars's detectors, the long silence that followed was filled not with absence, but with the slow emergence of understanding. The data that had once seemed impenetrable, vast blocks of electromagnetic readings, plasma densities, and photometric records, became a language of their own. Each waveform, each spike, each spectral anomaly told a different part of a single, intricate story. And within that story lay hints of processes so far-reaching that they redefined the cosmic continuum between chemistry, energy, and structure. Months after its disappearance, scientists began analyzing the interaction of 3I Atlas with the heliospheric boundary fields, using data captured as the comet crossed from deep interplanetary space into regions dominated by solar magnetism. What they discovered startled even the most seasoned plasma theorists. The comet appeared to have induced small, measurable shifts in the heliospheric current sheet itself. This was not a mere perturbation of solar wind density, but a genuine modulation of the sun's extended magnetic field lines. The object's plasma tail had functioned as a temporary conductor, an antenna stretching millions of kilometers, that subtly redirected local field orientations. Such behavior suggested that even small interstellar objects might act as dynamic agents in shaping heliophysical environments. For a brief time, 3I Atlas had literally rewritten a portion of the solar field structure. These interactions provided the first empirical evidence that visiting bodies could leave magnetic footprints within stellar systems. Some theorists speculated that over eons, such interstellar visitors could weave a faint lattice through the galaxy, a web of charged traces linking suns together, not by gravity, but by the cumulative memory of passage. Equally remarkable was the discovery of what came to be known as luminal drift signatures. When analysts synchronized optical data from Mars with concurrent Earth-based observations, they noticed microsecond delays between brightness peaks at different wavelengths. These lags could not be explained by instrumental timing errors or atmospheric effects. The conclusion was that the comet's light was refracted through variable density shells of vapor, each acting like a miniature lens that delayed specific frequencies. The pattern of delay mapped directly to molecular weight distribution, giving researchers a new way to read the composition of cometary gases simply through light arrival timing. This discovery opened an entirely new domain of remote sensing. Instead of relying solely on spectral intensity, astronomers could now analyze the temporal behavior of light to extract chemical signatures. It was an unintentional gift from 3I Atlas, a new observational tool encoded in its own luminous fluctuations. Meanwhile, the analysis of the comet's dust motion yielded another mystery. During the later stages of its approach, several high-velocity grains were tracked curving backward against the direction of solar radiation pressure. This defiance of expected dynamics could only occur if those grains carried strong electric charges and were responding to a transient electric field generated by the comet itself. The implication was that 3I Atlas temporarily functioned as an electric dipole, capable of accelerating particles through potential differences across its nucleus. If correct, the comet was a natural generator, an electrochemical system where sublimation, sunlight, and plasma flow combined to produce current. For planetary scientists, this hinted that other comets might possess similar charge-driven behaviors, helping to explain erratic jet patterns and bursts observed in their tails. But for physicists studying cosmic electricity, 3I Atlas became a keystone example of energy self-organization, a wandering dynamo crossing interstellar voids, gathering charge as it moved through varying plasma densities, and releasing it explosively under stellar influence. One of the most subtle yet profound findings emerged from radiative transfer analysis conducted years later. Hidden within the spectral noise of its tail were faint, repeating sidebands, frequency shifts too regular to be random. When modeled, they corresponded to vibrational transitions within crystalline ammonia hydrates at temperatures hovering near the triple point of water. That combination, ammonia hydrates oscillating near this threshold, suggested that portions of the comet's interior were maintaining quasi-stable liquid microphases even as the surrounding material froze or vaporized. Such fleeting pockets of transient liquid water ammonia mixtures represented ideal conditions for catalytic chemistry. The data implied that, within 3I Atlas's porous interior, microscopic zones of fluidity may have persisted for days or weeks at a time. In these tiny oases, reactions that require molecular mobility, such as polymerization, could occur naturally. This revelation was staggering. Even in the coldest, most hostile corners of interstellar space, there might exist moments of warmth and liquidity sufficient to drive complexity. Astrobiologists seized on this insight, proposing a new model of transient aqueous chemistry for interstellar ices. Instead of assuming complete stasis, they began to envision interstellar objects as pulsing between states of solid, liquid, and gas, driven by thermal oscillations during their long voyages. 3I Atlas had provided the first empirical evidence that the seeds of biochemistry might germinate not only on planets, but within the bodies of the comets themselves, hidden in brief intervals of thaw. Elsewhere in the archives, analysts uncovered data that redefined cometary optics. The scattering of sunlight from the halo exhibited unexpected polarization inversions, as if the grains themselves changed their internal structure under illumination. Computational modeling revealed that these dust particles could have contained phase change materials, tiny inclusions of amorphous to crystalline ice transitions. As sunlight heated them, they refracted light differently, creating flashes of polarization that mirrored solar pulsation frequencies. This optical metamorphosis transformed 3I Atlas into a living mirror of the star it orbited. The comet didn't merely reflect light, it modulated it, transcribing the sun's own flickering into optical symphonies visible across billions of kilometers. The full beauty of this process was only understood when Mars-based observations were compared with simultaneous solar data. Each pulse in the comet's reflected light corresponded to a solar oscillation pattern, implying that the comet's surface responded almost instantaneously to fluctuations in solar output. In effect, it served as a natural heliograph, writing the sun's heartbeat across the darkness of space. This phenomenon, solar echo scattering, offered a new window into solar dynamics, transforming distant comets into diagnostic tools for stellar physics. Beyond these measurable phenomena, the legacy of 3I Atlas reshaped cosmic chronology itself. By integrating isotopic data from its observed emissions with models of galactic chemical evolution, scientists concluded that the comet's molecular composition predated the formation of the solar system by several 100 million years. This meant that some of its atoms had circulated through at least 2 generations of stars. Born in supernovae, condensed into molecular clouds, then frozen into the nucleus of a wandering fragment. This discovery deepened humanity's sense of temporal scale. 3I Atlas was no simple traveler. It was a relic of ancestral suns, a messenger bearing the ashes of cosmic history. The carbon in its ices had once burned in the core of a long-dead star. The nitrogen in its gases might have cycled through ancient interstellar clouds before condensing again. Each atom was a storyteller, carrying memory older than Earth itself. The recognition of such continuity inspired a new branch of study, stellar genealogy of matter. Researchers began tracing isotopic families across cosmic samples, building maps of how specific atomic ratios journeyed from one stellar epoch to another. Through this lens, 3I Atlas became a genealogical record, a physical link between extinct suns and the living systems that would one day ponder them. As the comet's materials mixed into the interplanetary medium, Mars's instruments continued to pick up diminishing traces of its passage for nearly a decade. Each detection was fainter than the last, yet each carried faint reminders of its complexity. The delicate molecular fingerprints of methanol, cyanides, and carbon chains drifting through the solar wind. Those remnants were cataloged meticulously, serving as a time capsule for future missions. If you like this video, please give it a like and subscribe to our channel. Also, leave your comments below and tell us. What are your thoughts on 3 EMPA Atlas's Mars images? Do you expect shocking or exciting discoveries? We want to hear from you. Thank you for watching and see you next time.